All right, so let's get started with day 2 of this workshop. Day 1 was finished yesterday. So those of you who did not attend, you should have received a recording. In fact, all of you should have received the recording of yesterday's workshop. Yesterday was much longer than what we had anticipated. It was for a duration of 3.5 hours. And still we have a lot of things to cover, which we will be planning to cover in today's workshop. So let me do a quick recap of what all we have seen so far. We started the workshop with this aim of building a nutritional chatbot. But the catch was we wanted to build this chatbot which is grounded. And when I say grounded, it means grounded in some sort of a knowledge base. When we think of RAG systems, there always has to be a knowledge base. In our case, the knowledge base is this human nutrition PDF. So if we want to build a chatbot which is grounded in this knowledge base, we saw that we cannot simply make an API call to the LLM and pass the entire PDF in the context. That's because the PDF can frequently become much larger than the context size. So that will lead to hallucinations as one major problem. So retrieval augmented generation, or RAG, one of the main issues which it solves is this problem of hallucination. And the way it solves this problem is, instead of passing that entire PDF as the context, we pass only relevant bits of information from the PDF, which are related to the query which has been asked. So when I say we pass, it's a fancy way of saying this is we retrieve relevant information. That's where the retrieval part comes into picture. And we are using an LLM for the generation, but the generation or the prompt is now augmented or modified with the retrieved context. That's where the name retrieval augmented generation comes from. We saw that one simple way to think of RAG is giving an open book exam where you have the book at your disposal, and to answer a question, you of course rely on whatever you have studied so far, which is similar to a pre-trained LLM. But at the same time, you can open the book, go to particular page numbers, and retrieve relevant information, which might help you to give the answer in a better manner. Another thing which we saw is that, let's say, RAG of 2021 was simply to prevent hallucinations. But now RAG is a subset of this broader field, which is called as context engineering. So one doubt many people had was, as the context window of LLMs goes on increasing and becoming larger and larger and larger, would RAG become extinct? I don't think it will become extinct, because even if the LLM can take an entire PDF, it's not in your best interests as an engineer to pass that entire PDF. Why? Because cost is also an important parameter to consider, right? You don't want to bring an elephant to kill an ant every single time unnecessarily. That will be prohibitively expensive for the client for whom, let's say, you're making the RAG pipeline. So this entire workflow which we are looking at is built into steps or parts. One major part is file parsing, which we saw in yesterday's lecture. Second major part is chunking. So if you scroll down below, you'll see that we have seen document pre-processing, and we saw different types of document pre-processing. This was our first engineer's choice section. We saw PyMu PDF, we saw Tesseract, we saw Dockling. We saw the trade-offs between these three. I hope all of you remember these trade-offs. Then we started looking at chunking. So halfway through yesterday's class, maybe at around 1 hour 30 or 1 hour 45-minute mark, we had finished file parsing. And then the rest of the class was spent on chunking. We explored 5 types of chunking in a lot of detail: fixed size chunking, semantic chunking, recursive, structural, and LLM chunking. And we saw the trade-offs between all of these. We saw the trade-offs theoretically, and we also saw the trade-offs in code. So if you remember, we had a code which was titled chunking strategies, right? And towards the end of this code, what we essentially saw was figures which looked something like this. Towards the end of this code, we saw figures which looked something like this. We We plotted the average chunk size, the number of chunks, and the size variance across the different chunking strategies. That's one way to evaluate whether our chunking method is correct or not. But this is a statistical way. The better way to evaluate is go through the entire pipeline and look at evaluation metrics towards the end for all the chunking strategies. The backbone of this workshop is this code base which I have shared with you. And in fact, before going any further, I would encourage all of you or tell all of you to run the initial code blocks till the time we had finished running in the previous lecture. So in the previous lecture, if you remember, we had run until this point in time or this point in the code. We had run until here, until this point. We had not started any sort of chunking. So let's go ahead and run these different code blocks right now. I hope all of you have access to this code file. Let me share the link to the code file in the chat. All right. So now that all of you have this code file, before I go to the whiteboard again, I just want all of you to run until the point we finished yesterday. So to do a quick recap, these were the packages which we loaded. Then here is where we had ingested our PDF. We opened our PDF, and then we are maintaining this list called pages and texts. This list, each element of this list is essentially a dictionary. So each element of that list looks something like this. Each element of the list has the page number, the page character count, word count, sentence count, token count, and the text on that page. And then we had even seen a random sample from this pages and text list. So if you see page, this is one sample, for example, or two samples rather. This is one element of this list. This is the second element of the list, etc. And then we also actually saw some statistics on the text. For example, we saw that on an average, the number of tokens on each page was around 287. Why did we see this? Because later when we do chunking, we just need to keep in mind that if we want to use certain sentence transformers, their maximum input token length for their embeddings might be restricted to 384. So we just make sure that we are less than that overall. That's it. We have finished only up till here. So we are going to start after this point in today's lecture. So I'm again going back to the Miro board. Yesterday, we saw all of this document pre-processing, different types of chunking. And we ended yesterday's lecture at this point, I think. At this point where we had an engineer's choice section on which chunking strategy to use in what situation. And then we also had class questions such as which chunking strategy to use at which application. I think many of you answered these questions very well, but some of you also did not answer anything on the chat. So for those of you who did not answer, just make sure that internally you know the answers to these questions. That will make sure that your understanding is correct. So before we get started with today's lecture, let me check if there are any doubts or any questions in the chat. I will be sharing those who have registered just recently, I'll be sharing the recording with Krishna. Okay, if you have not received the recording, you can just email me, I'll share it across. And there is a question across 10 different PDFs. So you don't need to make 10 different RAG systems. Just have all of the PDFs in your database and just make one RAG system. Is everything clear until this point? Can all of you mention on the chat that are we okay to proceed? There are a number of things which we have to cover. Okay, good. It's clear, right? So today, let me give you an overview of what all we have to cover. First, we have to proceed in our current code and we have to do chunking in our current code. We are going to do sentence level chunking. Then what we have to do is that after that is done, we have to go to part number 4, which is embedding the text chunks. And after that is done, we have to go to part number 5, which is retrieval, part number 6, which is generation, and part number 7, which is augmenting the generation with retrieval. So that's the whole RAG pipeline essentially. This is our plan for today. After this is done, we also have to cover evaluation and we have to build this production ready system. So we will move ahead in an efficient manner. Okay, so let's get started now. So what we are going to do first of all, did everyone run until this point in the code? I have finished running until this point, and now we have to start from this further text processing part. Okay, you have run until this part. Okay, if you're still running, that's fine. Meanwhile, someone has asked a question that I have hit my GPU limit. Should I switch to run pod? Yeah, you can switch to run pod, Madhusudan, because there is a point where we are going to use GPUs today actually. So now what we are going to do is that in the code which we are following, we are going to do sentence level chunking. Can someone tell me, first I'll tell you the strategy which we are going to follow, then you can tell me which of the 5 types it belongs to. Okay, what we are going to do is something very simple. We are going to look at each page. We are going to look at each page. Let's say this is my page. I'm going to collect 10 sentences. That will be my one chunk. Then I will collect the next 10 sentences. That will be my second chunk. Whatever remains will be my third chunk. Then I will go to the next page. So I will make chunks of 10 sentences. Which type of a strategy is this? Among the 5 strategies which we saw yesterday. Fixed size chunking, right? It's the simplest strategy, is the fastest strategy. So let's go ahead and implement this in code. First, I want to make sure that everyone has reached this point along with me. How many of you have reached this point? This is to make sure that I don't go ahead too fast. Still running. Reached. Okay, so some of you who are still running might reach quickly. So let's get started. In order to make chunks of 10 sentences each, first we have to divide the page into sentences, right? So what we are going to do next is that this list which we have, for each page, if you remember, we have a list. Sorry, for each page we have a dictionary like this. We are just going to add the sentences also over here. Sentences on that page. And then we will see how to chunk it. But first we will add sentences to this dictionary so that later we can chunk it in an easier manner. So this is how our chunking process is going to look like. We are going to group 10 sentences into one chunk. Whatever remains on that page will be the remaining chunk. So now let's go to code. First, we need to break down pages into sentences, right? So we are going to use a package which is called as Sentence-Sizer from Spacey. What this does is that it just takes any document or a group of sentences and it breaks it down into sub-sentences. So for example, if this is a group of sentences, this sentence-sizer will break it into individual sentences. Now what we have to do is that we have to do the same thing for our list. So our list is called pages and texts, if you remember, and each list has the dictionary of every page, as we have seen. What we have to do is that we have to look for each item, which will be each page in our list, and then we have to add a key called sentences, and then just add all the sentences in that page. So run this right now. And then if you inspect a random element from this list, you will see that it has all the other things which we saw yesterday, page number, character count, text. But now it also has another key which is called as sentences, right? So here we have taken each page and also collected the sentences on that page. Okay, good. But this is still not enough. First, actually, let's do something like this. Let's look at the average number of sentences on each page. So average number of sentences on each page is around 10, which is good, right? So I can cluster 10 sentences. And again, I will make sure that the token count is 287. So the embedding model which we are going to use is this one. All MPNet base V2. The embedding model which we are going to use is this one. And again, I will share the link in the chat. I shared it yesterday also. This model has this limitation that the input is actually should be 384. And they have mentioned this in small font over here. Input text longer than 384 word pieces will be truncated. So now what we have seen is that if we are going to take 10 sentences into one chunk, uh, 10 sentences is roughly the length of a page. As we can see, the average number of sentences per page is 10. And we have already seen that the average number of tokens is 287. So if we create chunks of 10 sentences, we are kind of sure that most of the chunks will be less than the token count which is required by this embedding model. So here you can see the per sentence token count, which is 10. Okay. Now what we have to do is that currently we have this pages and texts kind of a list, right? Now we have to make a list which is called as pages and chunks. So essentially every item in our new list will correspond to each chunk. So earlier, every item in the list correspond to each page, right? Now what I want to do is that I want to have chunk number 1, I want to have chunk number 2, I want to have chunk number 3, etc. And in each chunk, you can think of it as a list which will have all of these parameters. You will see the page number on which this chunk is. You will see the sentences which are present in this chunk, etc. So here we are doing the grouping on a chunk level instead of on a page level. This is just to make sure that later embedding becomes very easy for us. Remember, we have to take every chunk and convert it into embeddings later on. So what I'm doing right now is that this pages and text list which was there, now I'm having this pages and chunks list. So you can think of it as each element now corresponds to every chunk. So if you look at the fifth element of this list, it will be the fifth chunk. It will give me the page number on which this chunk appears. It will give me all the sentences, all the 10 sentences in that chunk, for example. So this is called splitting each chunk into its own item. So just run this and okay, I've got an error called sentence chunks. I think I did not run something before. Yeah, I did not run this before actually. So once we augmented the pages and text with this sentences key over here, with the sentences key, what we have to do is that we have to group the 10 sentences together into each chunk, right? So what we are doing here is that we are going through each page and then we are doing that chunking as we have seen over here. Like this. We are going through each page and we'll make chunks of 10 sentences. That's being done in this step. So now my pages and texts will have sentences, that's fine, but each page will also have the sentence chunk, which is the collection of the 10 sentences. And after this point, I will make each chunk into its own item. So once you run this, then you will have a list which is called as pages and chunks. And if you inspect each element of this list, you will see that each element now corresponds to a chunk. So for example, this chunk which I've printed here is on page number 191. It has these sentences associated with it. The number of characters in this chunk is this much. The number of words in this chunk is this much. The number of tokens in this chunk is, let's say, 300. And then you can print an average of the statistics, right? So on an average, you will see that the number of tokens in a chunk is 183 and standard deviation is 111. So if you take a look at each chunk, it will definitely satisfy this 384 capacity, 384 word pieces capacity which we saw in the sentence transformer we are planning to use. And this I have also illustrated over here. So until now, think about the fact that we have access to each chunk now, and we can further see what are the sentences within each chunk, what are the characters in each chunk, what are the words, and what are the tokens. And we are printing out these statistics over here just to make sure that each chunk, the size of each chunk is less than the input embedding dimension required for this sentence transformer. Now, one thing which we notice over here is that there are some chunks which have very low token count. Can you try to think where do these chunks come from? Why are there some chunks which have only 3 tokens, for example? Yeah, if there is some footnote or end of page or subtitle, remaining items, all of these are correct answers, right? So technically, we don't need these. We don't need these chunks. We can remove it because they don't add any useful information. So what we do is that we keep a minimum token length for every chunk. And then we create this new list called pages and chunks over minimum token length. And here what we will ensure is that every chunk will have the number of tokens which is greater than 30. So until this point in the code, we have ensured that we have access to chunks and every chunk will have token count which is greater than 30. Roshan is asked, how do we handle chunks when the size is greater than 384? That's a good question. And in this case, I'm willing to let this go because even if you take within one standard deviation, right, it's still less than 300. So the amount of chunks which I'm missing out are very low. So I'm willing to take this trade-off over here. And in fact, when I say missing, this will not be completely neglected. What the embedding model will do is that it will truncate it to 384. It will just remove the remaining tokens and truncate it back to 384. Keeping the footnote chunks could be useful as well. Yeah, we can do more granular level chunking here. So if you see that some chunks which have this minimum length are in the footnotes, you can write a specific code to retain the footnote chunks. But here what we are doing is that as a blanket thing, we are just getting rid of all the chunks which have less than 30 tokens. The point I want to illustrate here is that if you directly use packages like LangChain or LangGraph or Llama Index, all of these things are usually missed. But mostly on industrial problems, you need to do custom chunking like this also. So until this point in our whole RAG journey, what we have is that we have this. I'll take a screenshot of this. We have this list called pages and chunks over minimum token length. Do you understand what this list represents? Essentially, this list, every item of this list will be a dictionary corresponding to a chunk. Every item, so the first item will be chunk number 1, the second item will be chunk number 2, etc. Why am I doing this? Because later when I want to convert each chunk into an embedding, what I do is that I just go to this chunk 1, I look at the sentences in that chunk and I just convert it into an embedding. So then accessing the sentences within each chunk will just become much easier. There is a question, can't we use index to group the related? I'm going to come to that. I have not covered the concept of indexing so far. Oh, you mean the index in the table of contents itself, is it? Like the index in the chapter, index in the book. Yeah. So that will be structural chunking. As we saw yesterday we actually did structural chunking, right? But it has its trade-offs. I'm going to explain this to you. This whole code which I'm showing right now, right? I have also run this same code using structural chunking end to end. And there are some trade-offs with this approach. Not everything is structural chunking looks to be the best way to proceed for this book, right? Because chapters are small and every chapter has constrained information, but there are trade-offs. There are computational trade-offs. I'll get into that. For me, 75% says 400 is the token count. No. So 75% says 400. That's fine. Uh, that does not mean transformer won't be able to read 75% of the chunks. The transformer length is cut off at 384. So the only metric, Anita, you should look at in this table is mean and standard deviation. As long as your mean plus standard deviation is roughly less than 384, you are generally fine. You won't exceed that length too much. Instead of setting chunk size to 10 sentences, why can't we set it to 384 words? We can do that, Sanjeev. That's also completely fine. In fixed size chunking, you have an option to do whatever you want. Currently, I've just bucketed it into sentences because if you do word wise, some sentence might get cut. And in this, I have not even used an overlap over here in the code. We can do that. We can use an overlap also if needed. Did everyone understand until this part what all we have covered so far? Until now, what we have covered is that we have this whole book, right? Which has around 1200 pages. We have divided that book into chunks. And next, what is going to happen is that in the next step, these chunks are going to be converted into embeddings, which means that these chunks, which I've highlighted right now, each of these chunks are going to be converted into vectors. So the whole idea is that whenever a query comes, and that query is also converted into a vector, later I am going to get the retrieved items or relevant items based on this query vector and how similar it is to these embedding vectors. That's the whole idea. So the next step in our journey, which is part 4, is embedding the chunks. There is a question, pages and chunks over minimum token length still shows the page number. Yeah. So that shows the page number. We don't need that page number anyways. So we have not got rid of it really. Is the chunk not mapped to the chunk ID? So the chunk is actually mapped to the index of the list. The advantage you have of maintaining a list is that if you access the fifth element of the list, that will be the fifth chunk. The chunk is not mapped to the page number right now because we are not doing structural chunking. We have just put 10 sentences, put them in one chunk. Then the next 10 sentences, we have put them in the second chunk like that. And we have put it in a whole list. So if you want the 500th chunk, you just access the 500th element of this list. So are we good to move to the next part, which is embedding? Has everyone understood until this? In real settings, is there a cleanup of the PDF? Yes, there is. And we have also done a cleanup if you see. We have done a text formatting which removes white spaces. There can be a much more deeper cleanup if the text is really messy. How does overlapping help here? Overlapping will help because it preserves the context. Remember, we saw this yesterday also. In fixed chunking, overlapping always helps because overlap ensures that some context is retained. All right, everyone. So we are almost halfway through this RAG pipeline, but now comes a very important step, and also the step which is not paid too much attention to because there are a lot of trade-offs to be made in this step, which I'll come to right now. And I want to make all of you aware of the trade-offs. So what we have done, as I mentioned, is we have this document that is fine. We have pre-processed text into smaller chunks. And now we have these chunks which are ready, right? The next step is to convert each chunk. So we have, let's say, 2000 chunks. We have to convert each chunk into a vector embedding. And To do this, we are going to use a sentence transformer, which is all MPNet base version 2. Now, before we actually go to the code, I want to explain a few things about how to do the vector embedding itself. There are three things which you need to consider to do a vector embedding. Actually, I'll explain that after we run the code. So I have this engineer's choice section. I'll come to that once we do the embedding for our chunks. So can all of you go to the code right now? Here, what we are going to do is that we are going to load this all MPNet base version 2 model, and we are going to convert the all of our chunks into vectors um, using this sentence transformer. So this is again provided by Hugging Face, and it's only 500 MB. It's not a large model, so this should not take too much time. And what I have done here, just to give you an idea of how the embedding really works, is that we have taken some random sentences, and I've printed out the embeddings over here. So let's say if you take a look at this sentence, the sentence transformers library provides an easy and open source way to create embeddings. This has taken this sentence and converted it into a 384 dimensional vector. Similarly, if you look at the second sentence, sentences can be embedded by one by one or as a list of strings. This has again been converted into a 384 dimensional vector. But the main thing is that you can even convert single sentences into vector. The key thing to realize here is that these vectors really carry meaning, which means that these sentence embeddings are not done in a completely random manner. If you have a sentence, right? If you have a sentence, and this is the key idea behind retrieval augmented generation, without which this technology itself would not exist. If you have a sentence in a vector space, and if you have another sentence in a vector space, sentence transformers or the model which we are using retains the meaning. So sentences which are closer in meaning, their angle will lie closer to each other in the vector space, or they will have a higher cosine similarity score. Whereas sentences which have complete divergence in meaning, their cosine similarity score will be the lowest. This is the main thing which we are going to exploit. We are going to convert sentences or chunks into vectors, and we are going to use the fact that vectors actually carry meaning to understand. So you might be thinking that when a user asks a prompt, how do we retrieve relevant information? The relevant part comes from understanding how close the vector embeddings are. That's the mathematical notion of understanding relevance between sentences or relevance between paragraphs, let's say. So now what we can do is that you can scroll down below, and I'm going to show you uh, three things actually. So I'm going to show you embeddings on a single CPU. In this, what we are going to do is that we have 1680 chunks, right? We are going to convert these 1680 chunks into vectors on a single CPU. We are going to see the time it takes. Then what we are going to do is that we are going to convert these 1680 chunks into vectors, but on a GPU. And the third thing which I want to show you is that we are going to do the embedding on GPU, but we are going to do it in batches. And let's actually see the time taken for all of these three. So in this part, just check what we are doing. We are going through each element of these pages and chunks over minimum token length list. We are accessing item, and then we are accessing embedding within the item. So run this right now. So we are actually accessing sentence chunk within each item. Remember now, every dictionary has the sentence chunk associated with it, which we have seen. If you scroll above, every chunk will now have the sentence chunk. So what we are essentially doing is that we are accessing the sentence chunk, and then we are doing a for loop, and we are converting every single element of that list into a vector embedding. So there will be 1680 uh, vector embeddings right now. So if you have, let's say, what we are right now doing is that if you have 1680 chunks, if you have 1680 chunks, all of these 1680 chunks are getting converted into, we use a different color here. All of these 1680 chunks are getting converted into a vector embedding. Whose size is 384. Let's see if there are any questions in the chat. Every chunk will have an embedding. Yes, every chunk will have its own embedding. There are 1680 chunks, so there are 1680 embeddings. Where is the number 1680 coming from? So the number, if you scroll above, the number 1680 is coming from so actually the number of chunks which are present in pages and chunks or minimum length is 1680. The total count before we removed the chunks of low tokens was 1843. After that, it's 1680. We have not printed it over here, but the number of chunks which we have is 1680 now. That's where that number is coming from. Then there is a question from Jaydeep about what's the wall clock time. So wall clock time is a terminology which is used for benchmarking GPU runs. And it's basically as simple as if you have a stopwatch or if you have a clock on the wall, how long does it take? It's as simple as that. That's where it's also sometimes called wall clock time, because there can be multiple times, right? There can be the actual processing time within the CPU itself, but the wall clock time is the most understandable to users. How do we get one embedding for all the sentences? Now that's a great question, Gaurav, and we have covered this in the earlier lectures of our class. It's very different from word to vec. A transformer comes into the picture here. The main idea of a transformer is that it can take an entire paragraph, retain the context, and convert it into a vector. You might be thinking of word to vec, right? Where words or tokens are there and it's converted into a vector. That came in 2014. Word to vec came in 2014. Transformers came in 2017. And transformers can take paragraphs, entire paragraphs, and they can convert it into vectors. How can they do that? Because they retain context. How can they retain context? Because they have the attention mechanism. So all of that is kind of linked. When I'm saying sentence transformer here, it is built on the attention is all you need paper, not on the word to vec paper by Google. That's a nuance to keep in mind. Why is it different from CPU time? This because the CPU might finish operations earlier and there might be some time taken for display, let's say. There might be some additional time overheads. If you just want to take the processor time, even in transformers, we do token level embedding. Yes, we do. So we do token embedding first, then pass the whole thing to a transformer and then uh, see what comes out. So there is one output vector also which comes out, and that contains the information of essentially whatever you have passed in. But the first step, you're right, is a token embedding layer. Jaideep is saying wall time is less than CPU time. Are you pointing to this code? Oh, this 18 minutes 7. So I'm not sure what this is actually, because this does not make sense right now. But ideally the CPU time is very different from wall clock time. I don't know why it's saying 18 minutes honestly right now. There is something which needs to be checked here. But if you check the wall time for CPU embeddings, it's 4 minutes 32 seconds, right? Now with just one simple change, we are passing the embedding model to CPU in the first case. In the second case, we are passing the embedding model to CUDA, which is GPU. So someone had asked at the start of the lecture that their GPU credits are over, right? The only place where you will get stuck if your credits are over is this step, because we need to be connected to a GPU instance for this. So then what we can do is we can also check the wall time for GPU embeddings. Okay, so there are many questions in the chat related to how much context can an embedding of size 1K preserve for text with thousands of tokens in it. So that usually embedding size is very different than the input context which a transformer can handle, and that's usually mentioned in the library card. For example, this transformer, uh, actually I have been mentioning 384 dimensions, right? This transformer actually converts it into 768 dimensional space. So that needs to be corrected. We are not, if we check the output dimension, it's 768. Yeah, but to your question, many of the embedding models which you see, they do mention the output dimensions, but somewhere you will see the input constraint is also mentioned. So see here it mentioned input text longer than 384 word pieces is truncated, because this is a sentence transformer. If you take an embedding model made by Gemini, they usually don't have such uh, constrictions. So for example, if you go to the leaderboard, right? This is the MTEB leaderboard of Hugging Face, and I'll paste the link in the chat also. Okay, so if you see the Gemini embedding now, here these are huge embedding models compared to what we are using right now. They can even take multiple paragraphs because the context is preserved much better here. So if you go to Qwen 3 embedding 8 billion, we can check if there are any instructions with respect to the input size. Usually models which have context limitations have instructions with respect to that. Uh, so I think Mayank has answered this question which Jaideep has asked. Basically, why is the CPU time here 18 minutes, right? Whereas wall time is 4 minutes 32. So Mayank has mentioned that CPU time sums all the multi-threaded processes, whereas wall time is real world time. So I hope Jaideep that answers your question. Do you foresee it necessary to fine-tune an open source embedding model? It depends actually. We are considering doing that for an application of Diana route which we have. But for all practical purposes, usually not needed. How does it work if my text contains numerical data? Suppose I generate embeddings from product descriptions that also include price, like will embedding alone is able to handle. So if you use embeddings from powerful models, Sanjeev, so if you know that your text is going to have numerical data, then of course you should not use this sentence transformers because it's meant for paragraph level sentences. Then I would highly suggest you to use Qwen embeddings, because these are similar embeddings they used for the Qwen LLM also. So I'm sure they will have provision to deal with numerical data. They will be dealing with numerical data in a much better manner than sentence transformers, for example. In that case, you might want to go with a model which has a higher embedding dimension, let's say, or use an embedding model which is specifical for numerical data. So let's check actually. I don't know if it exists. I am not sure if there is an embedding model specifically for numerical data really. But until that, the best option is to go ahead with large embedding models provided by Qwen or Gemini, let's say. Why is it taking more time for some people? It depends, I think, on the configuration which we have really. For me, if you see, so one thing which is the takeaway from this part I want to mention to all of you is that CPU time, if you check CPU wall time is 4 minutes 32 seconds and GPU wall time is 26 seconds. So you see the amount of difference here, it's almost 10 times. GPU time is 10 times faster. Now what we can do is that we can also collect all the text chunks and pass to the GPU as batches. So one batch will be so batches will be processed parallelly. So if you run this now, this is here we are doing GPU embedding itself, but what we are doing is that we are uh, breaking down our chunks into batches of size 32. And here there is a hyperparameter which is called as the batch size. Um, So here wall time for me was around 24 seconds. Let me run it once more. It did not improve the time that much. Can all of you mention your time for this batch GPU embeddings? What is the time which you are getting for batch GPU embeddings? 24. 23. I am also getting around 23 seconds. It's not as good compared to uh, CUDA, just single GPU, right? So already you all must be seeing that GPU plays some crazy tricks. And all of this is related to GPU programming. Every single thing which we are seeing here has some meaning. It's just that we need to know how GPU programming works. So this is the reason I keep on referring to this playbook. I referred to this in yesterday's lecture also. To gain a mastery on parallelization and fast computing, we all need to know, and this is extremely complex. It's not simple at all to know. There are four types of parallelism basically. There is data parallelism, there is pipe tensor parallelism, there is context parallelism, and pipeline parallelism. But anyways, I've shared this link again, but I'm sharing it today right now. I want to make a course on this once. Yeah, expert parallelism is the fifth. So it's like 5D parallelism. This is for people who are interested in this. Others don't get confused by this or don't get intimidated or scared by this at all. It's not really related to the RAG workshop which we are doing right now. I just wanted to bring your attention to these three types of embeddings which you can do. Normally, again, when you directly use libraries, everything is abstracted away. But remember that there are three ways to convert chunks into embeddings. There is a normal CPU way, there is a normal GPU and batched GPU. And ideally, the speed increases from left to right. Next, what we are going to do is that once we generate the embeddings, we are going to save them to a file which is called as text chunks and embeddings data frame.csv. And then we are going to see the file. Now, pay very careful attention to this file. Each element here is a chunk. So this is my first chunk. It has the sentences in that chunk. But check this last column here. That's the embedding column now, which is added. This is what is meant by creating embeddings for every chunk. So now if you see, I have these vectors which are stored in a file, right? For every chunk, I have vectors which are created and they are stored associated with it. And this entire thing I'm saving in a file called text chunks and embeddings.csv. Now this again, how has everyone run until this point? Can you mention yes in the chat? This is an important checkpoint in our code where embeddings have been generated and they have been saved to file. Okay, good. Now there are a number of engineering questions which present ourselves over here. Once we have saved embeddings to file, the natural question is that two questions actually, right? And we should spend time discussing both of these questions. The first is which is the embedding model which I should use? And the second is where should I really store my embeddings, right? Both of these are very important questions. Not just many people just ask this first question. And for the second question, they randomly use a library like Pinecone or VV8, whatever. But both of these questions need to be asked, and I'll answer each of these. So there is no simple answer again to both of these questions. For the first question, there are four things which you usually have to consider, right? Of course, you have to consider the size of the input. So if you want to embed longer sequences, choose a model with larger input capacity. And sometimes input capacity is not mentioned for the model. At that time, just go ahead with very strong players like Gemini embedding models will have very large input capacity for sure. You can go with Gwen 8 billion embedding models, which I showed you on the MTEB leaderboard. Where can you get these models? All these models and the size of these models are available on this leaderboard, which whose link I'll again share in the chat. Uh, yeah, so first is size of the input. The second is size of the embedding vector. Now, there was a question in the chat, I think by Sanjeev, that if my data has some numerics or some information which is not simple text, then general thing is that the larger embedding size is a better representation. So generally go with larger embedding vectors if your data is a bit more complex or challenging. But remember the trade-off here, that takes more time to compute and that takes more storage time also. Again, here larger models generally result in better embeddings. This I mentioned earlier also, that these models which come at the top, right, they are huge models. This Gemini embedding 001 and Qwen embedding 8 billion, they are large models. They take up a lot of memory, but performance wise they are amazing. So just check that as another metric. And the final metric is again open source or closed source, right? That's another important thing. We use sentence transformers right now, fully open source. Many models, many embedding models are open source, but if you go ahead with OpenAI embedding models, they are state of the art for sure. So for example, OpenAI provides some amazing embedding models, which we have used in our industrial projects a lot. When cost is not a concern for the client, right? You can use OpenAI embeddings, text embedding 3 small, text embedding 3 large, etc. But these are closed source models, so they will be a bit more expensive. They also mention maximum input, by the way, over here. So that's the four axes of trade-off which you need to consider. What is meant by input capacity? By input capacity, I mean the number of tokens you have in each chunk. How do you calculate the compute requirements? So usually it's a bit difficult to calculate exact compute requirements, but a good metric is if you go to a particular model, you will see the memory which is taken up by that model. So for example, here there is a metric called memory used. So if you see the first column here, if you see the first column here, that's memory used, right? And if you see for Qwen, it's 28866 and it decreases subsequently for simpler models. And number of parameters is also an important metric to consider when looking at how much compute it will take. Let's see if there are any other questions. But when you used OpenAI embedding models, how much flexibility that's the trade-off, Amit. So we cannot do anything about that, right? The main thing is that OpenAI has a leverage right now. The leverage which they have is that even though everything is abstracted away, some clients just care about performance, right? They don't care about, let's say, open source. Let's say you have a client who does not care about open source or closed source. They don't care about cost either. They just want the best performing models. For that, OpenAI is still the gold standard for many things. Only when you have clients who care about privacy, let's say you want to optimize on cost, then you start to look at other open source alternatives, let's say. Which embedding models to use if we are having code scripts data, right? Code scripts, again, use Gemini embedding. Qwen models are very good with codes. So you can use Qwen embeddings. Why are you considering multilingual? Yeah, we don't need to consider multilingual embeddings here at all. If the text is English. When you mean some embedding model is better, what do you mean? So when I say embedding model is better, it just means that it captures the underlying text in a better manner. So it captures nuances or context better. Let's say if you have one paragraph and another paragraph and they're not directly connected, but some deeper context is connected, a larger embedding model uh, will capture those nuances clearly. Or if you have a larger embedding model, it might capture numericals more clearly, or some amount of text, some underlying data which is not pure text. You will just get better answers basically, because in retrieval augmented generation, you need to rely on the model's ability to understand meaning, right? We talked about how these models which I'm showing you are essentially transformers, and they have attention blocks. They have the attention mechanism. So bigger models have more parameters in those mechanisms. They are just better in understanding context. So when you retrieve information from your data in the RAG pipeline, it will just be better with some embedding models compared to others, let's say. What about pictures, sentences, tables, numerics in a document? So many of these embedding models can deal with all of that. They are multimodal. For example, OpenAI has its multimodal embedding models. Many of the Gemini models which I showed you are completely multimodal. We are just dealing with this sentence transformer, right? But you don't need to stick with that. Many of these models, unless it would be mentioned whether it's text embedding, then it's only for text. But many of these are completely like they are multimodal. They can deal with images, etc. But you need to see in the document card for that model. Okay, now let me come to the second question, which is again of primary importance, is where should I uh, where should I store my embeddings? Now, does anyone have an answer to this? If I ask you this question that where should I store my embeddings, what will you respond with? So vector database is the first thing which comes to mind, right? But it's not intuitive. What is the intuitive thing which comes to your mind? So someone who has not studied about vector databases will not reply with vector databases as an answer here. Because normally we study databases in a different context. The simplest thing is that why not I just like store it as a tensor, right? In PyTorch. Why do I need a vector database? I'll store, let's say 100,000 embeddings in a PyTorch tensor. And we saw that now we have 1680, 1680 chunks. And each is 768 dimensions, right? I can just store these on file and I can store them in a PyTorch tensor. Why do you need databases in the first place? Yeah, np.array, right? Yeah, why not simple array? Why not a simple tensor? Embeddings are huge, but have we actually tested this? So Amit has mentioned an important point. I will encourage all of you to read that text because that comes from industrial experience. That in industrial setting, a single chunking strategy usually does not work. We can use simple SQL table. Exactly. So now as engineers who are taking this workshop, we need to think holistically, right? So the thing is, if you have got a relatively small data set, right? For example, if you have under 100,000 examples, even np.array or torch.tensor works perfectly fine. You don't even need to think of a vector database at all. No need to go with vector databases if the scale of your problem is not very huge. Vector databases only need to come into picture when you have 100,000 plus embeddings or a million embeddings or 10 million embeddings, let's say, right? So what is a vector database? For those of you who don't know, vector database is, so all of you know normal database, right? Let's say if you have a Firestore database, let's see. I think we do have a Firebase account, but I'll need to check it. So if you go to Firebase, right? And if I go to my Firebase console right now, uh, let's say I look at some project which we have, you'll see that usually GCP, AWS, Azure, they have databases, right? And databases, what database looks like, it's like, let me, yeah, it looks something like this. So if someone has registered, you can store their information over here. You can store how many times they're interacting with. So if there is a Zomato, yeah, like every application which you think about, they can have a database which tracks user logins. We can track whether someone has liked a certain post, etc. So all of this information is maintained in a database. Now, when RAG systems became popular, people started thinking of why can't we have separate databases for vectors, where the only thing which will be stored is vector embeddings. And the reason that made a lot of sense is because at that time, if you have, let's say, a million, let's say if you have 1 million vectors or 10 million vectors, you cannot just randomly store them in PyTorch. Because ultimately, remember what you have to do is that you will get a query vector, and you will need to find which of these 10 million vectors are most similar to the query vector. So you will need to traverse through 10 million vectors and find the cosine similarity score. And that just very, very difficult with PyTorch. So what do these vector databases implement which makes them faster? Does anyone know? Let's say I make a vector database. What do these vector database implement? Indexing, right? This is the main terminology which you need to understand when you think about vector databases. And this is not explained very well anywhere in literature. But the thing is, indexing actually just means that how are you going to get to the most efficient. So let's say instead of going through each of these 10 million entries sequentially, can I do some clever trick? So one trick could be something like this, which is called quantization based indexing. So basically, can I use clustering where I can uh, create clusters of common vectors? So whenever a new query comes in, I don't need to check my entire database. I just need to check within that particular cluster. That is one way to do an indexing. The second way of doing an indexing is essentially graph-based indexing, where let's say if you want to, in this approach, the indexing is just distance-based, right? If you get a particular query, you find that cluster which is most closest to that query. So that's distance-based indexing. The second approach is graph-based indexing. Let's say you want to find that element which is closest to this pink point. You randomly start from A, then you see where all A is connected to. So out of all connections to A, D seems to be the closest to ping point. Then you check the connections of D. Out of all connections to D, E is closest to the ping point. And then E has no other connections which are closer to the ping point. So you say that the closest is E. So see, within two simple steps, I told you which is the closest point here to this ping point. So what I did right now is exactly what indexing actually does. Indexing are clever methods to essentially find out uh, which of your vector is closest to the query vector. There are two approaches, cluster-based approach and a graph-based approach. And the formal way of describing these two approaches is something called IVA flat and HNSW. So in IVA flat, you can think of it like k-means type of an approach, right? Where you have a query point and there are clusters, and then you find which of the cluster is the closest to the query point. That's IVA flat. The second type is called HNSW, which is hierarchical navigable small words. This is a bit graph based. The way it works is that you get a query, you go to the top level of the graph first, you find the closest answer at the top level, then you go one level below. Then you go to another level below. The lowest level is a bit more densely packed, and here then you get the closest um, vector to the query vector, right? And there are trade-offs between IVA flat and HNSW. I'm not going into too much details of this, but just remember that IVA flat is clustering based. Think of k-means clustering, which you have already used, whereas HNSW is a bit more graph based. I showed you this graph based approach, right? But it's flat, it's just one layer. In HNSW, you have vertical layers. The top layer is the most sparse. You find the closest neighbor to the top layer, you come to the second layer, and then you come to the bottommost layer. And usually that has seen to have great advantages. I'll share this link also with all of you. So if any one of you wants to go into more detail about HNSW or IVF flat, just keep this in mind. Also, The reason I'm mentioning this is in one of the industrial project which we were doing, we realized that IVF, so there is a trade-off between these two. HNSW creates this kind of a multi-layered graph structure, right? So whenever a new data point is added, and we want to create an embedding, it takes a long time to create that embedding. So the index build time is higher and the memory usage is also higher. But once that HNSW graph is created and a query is asked, its retrieval time is much faster than IVF flat, and sometimes its performance is also better than IVF flat. So if you want to create something quick, then IVF flat, or by default, the default indexing option of many vector databases is IVF flat, but you can also choose HNSW if you want a better performance. Uh, are we trying to find the closest index in the embeddings? Yes, that is correct. So essentially, what I'm showing right now is that you have a query which has been asked. In the RAG chatbot, let's say this is the query, right, which I'm asking, what are the water soluble vitamins? That's the query. That is my query point. Now, when that query point is asked, I am looking at my indexes. I'm looking at my chunks. I'm looking at my chunks, but instead of going through all of my chunks, I will just look at clusters. I will just look at clusters and I will find that cluster which is closest to the query point. And then I will retrieve chunks from that cluster. That just makes the retrieval process extremely fast. And HNSW builds further on top of this, whereas where it creates this kind of a graphical graph visualization kind of a structure. It does not rely on centroid calculation. So it's less sensitive to the initial size of the data. It is very important for you to understand these inner workings of vector databases, because once you understand this, there are a number of applications built on top of this. For example, uh, there are three major, or I should say four major players offering, five major rather, offering vector databases. How many of you have heard of these? There is Pinecone, there is Qdrant, there is VV8, there is Milvus, and there is Chroma. All of these are vector databases. I have not used all of them, but I have used Pinecone, I have used Milvus, and I have used VV8 before. And the documentation of all of them is pretty much standard, right? So you can easily get started with Pinecone. You have to just, by default, it has an HNSW index, I think. And it directly creates the embedding of your database within 2 to 3 lines of code. Similarly, if you go to Milvus documentation, you can very quickly, in I think 5 to 6 lines of code, you can set up a vector database. And then when you ask, so these are the documents which can be embedded. You can specify an embedding function and very easily create that vector database. I am not showing you these libraries because we are following a from scratch approach over here. But my aim is that once you get through the workshop, accessing any of these libraries will become extremely simple. I'll just share the links of these libraries in the chat. This is Milvus. Then Pinecone also I showed you. I think this is Pinecone. There is a great question which is asked in the chat that how many of you have, so okay. Right now, what we have seen is that PyTorch is simple, but you can go one level further and create these indices, right? Now, when you create these indexes, you have two choices. You can simply offload everything to a vector database service like Pinecone. Let's say you offload everything, so Pinecone takes care of it. Or you just stay in Python and you use FAISS. So you use FAISS Python library. You don't create an account on Pinecone or VV8, or you don't create an account on Milvus, for example, but you just use your tensor and you apply Facebook AI similarity search in Python itself. So I don't know how many of you have actually used FAISS before. Yeah, right. So FAISS is just a library. Remember, there's a different, it's not a database. FAISS does not provide you with a vector database. Pinecone and Milvus, uh, or VV8 or Chroma, they provide you with a database. FAISS is just a library for efficient similarity search. That's the major difference. It can be used very simply, and I think it supports HNSW also. It supports IV. It by default comes with index flat L2, which is a distance based metric similar to the IVA flat which we just saw. But this is a library, so you can create your tensor in PyTorch and use this library. Let's say it does not give you a database directly. Whereas if you are building a RAG application, your vector database can be stored on Pinecone or your vector database can be stored on Milvus. That's the difference between these frameworks. Uh, can you explain how do we do best indexing while storing the embeddings? I always thought we are done while we create embeddings. Yeah, so we are not done when we, so that's abstracted away, right? So let's say when you create an account on Pinecone, the indexing is fully abstracted away by them. But what they are doing beneath the scenes is that they are creating clusters beneath the scenes. They are using IVF flat, or if you give a different indexing choice, they are using HNSW, let's say. But under the hood, they are kind of organizing your vectors so that retrieval becomes fast. It's just that there are now these 10-minute Pinecone tutorials. There are these 10-minute Milvus or Qdrant or Chroma DB tutorials where people just build that and think they're done with it. But under the hood, we should see what is actually happening behind these. Chroma DB also, I should point out actually. Yeah, this is also used by many. Then Qdrant is also very popular actually. This is a vector database. Then Pinecone I already shared with all of you. Okay, so these are the trade-offs which we need to consider when we think of embeddings, right? When we think of embeddings, first thing to consider is that are my examples less than 100,000? Then I'll go with PyTorch. Good. Second, if my examples are more, let's say 100,000, can I just use FAISS? Why do I need to create a separate vector database on Pinecone? If I want to offload everything to Pinecone so that my client can view my database, make it simpler for them, I offload everything. Vector database is created on Pinecone or Qdrant or Chroma. I get charged for it, but my service is taken care of. These are excellent providers. They're very popular. One more last thing which I want to discuss, which we are going to use for our production is so before that, let's see the disadvantages of using a vector database, right? I showed you, let's say you're building an application, right? Like a chatbot. And people are coming to your chatbot. People are logging in this nutritional chatbot, let's say. People are coming in, they're logging in. And you have created a Firestore database collection, which looks something like this for users who have logged in, let's say. Okay. On top of that, you have another database which is collected in Pinecone. This is for your vectors. So now you have to manage two databases. You have to manage one database for your users and how they are interacting, and you have to manage a second database. The issue with this is that, let's say you have some metadata which has been collected in your vector database, like we saw for sections, headings, subheadings, right? Similarly, if you in your metadata, if you see that a user is only asking certain set of queries, it becomes one more layer of difficulty to transfer that metadata from this database to the earlier database so that it can show up on your front end. The issue is that with two vector databases, the transferring of one vector database to the other vector database becomes difficult, especially with respect to metadata which you might be collecting. And again, now the issue or this issue, how do we solve this issue? Is there a way where I can have my vector embeddings and my database in the same database? So is there any way where I can put everything in the same data? I want my users, I want everything in my one database. And there is a way for this. And for that, we first need to know what Postgres is. How many of you know what Postgres is? Okay, many of you might be knowing, right? But some of you might not be knowing. Let's say something like Supabase. Now, Supabase is a Postgres development platform, which means it provides a Postgres database for you. And I have detailed instructions on what is Postgres SQL. So it is a relational database management system, basically. So let's say if you have your application connected to Postgres and user information, you are storing everything in this RDBMS, which is relational database management system, right? What if you can store your embeddings also in the same database? It's completely possible to do that, by the way. And the way to do that is using something called PGVector. It has 18,000 stars now, and it's a open source vector similarity search for Postgres. So essentially what you can do is that it's a Postgres extension in which you can have a database, and in that same database, you can have another column for your embeddings. What is the added advantage on top of this? Now everything can be accessed through SQL queries, right? And people have mastered SQL querying for a large amount of time. Everything is now in one database. Your login information, all other database, and your vector embeddings are also in that same database. On top of that, things can be accessed in a much faster manner using SQL querying. And as we all know, SQL, we have mastered SQL. Humans have mastered SQL. It's very quick, it's fast. So this seems to be solving the problems, right? So if you have a dedicated vector database like Pinecone or VV8 or Milvus, usually that is separate from the main database. So metadata needs to be synced manually. But in Postgres plus PGVector, it's the single database for structured data as well as unstructured data. And again, Postgres SQL is decades old, it's battle tested, it's reliable. Whereas if we use a dedicated vector database, it's less mature. And this again comes with full SQL support. You can use SQL functions like joins, filters, etc. SQL support is a bit limited to a dedicated vector database. So we are using this principle called as tea kettle principle. I'm not sure how many of you are aware of this. My maths teacher taught me this principle in 8th standard. So the main idea of the tea kettle principle is that if you are given a difficult problem, one of the best ways to solve that problem is to take it to a simpler problem which you have already solved. So SQL is a problem which we have already solved. Postgres is a problem which we have already solved. Why not take this problem to that place which we already have done before, right? Is PGVector as fast as... So PGVector also allows you to create indexes, right? That's the thing. PGVector, you can create different indices using PGVector also. Like you can create IVF flat, you can create HNSW, etc. Let me see if there are any other questions. You have to create extension vector, then create index. So you have to, when we are actually going to combine Supabase and this PGVector, we'll have to create an index on our own. We'll need to specify which index we have to use. Let's see if when we use a vector database and then there is a query by the user, the cosine similarity is calculated by a vector database or our embedding model. So that's the thing, right? Many of these vector database also provide you the functionality of providing your embedding model. So if you see Milvus, if you are planning to use a Milvus vector database, you can specify an embedding model also. If you check their tutorials or just check the get started quick start, here you can specify your embedding model. You can also create an open source embedding model over here. So basically everything can be integrated together if you use these frameworks also. Is it possible to write SQL queries? Yeah, 100% it is possible to write SQL queries to check similarity. We are going to do this in today's class actually. Uh, that's the advantage, right? It's definitely possible to write SQL queries to check similarities between vectors. It's not difficult at all. So in our recent industrial project, we went ahead with this approach instead of any vector database. We went ahead with getting the user data on Postgres and getting the embedding vector in that same database in another column. Actually, I think I might have my previous project here. I don't know if I deleted it or not. But if you take a look at our database, no, yeah, check this. This is what we are going to build today. But the advantage here is that we have all the other data, that is fine, but we also have the embedding vector in that same database in Postgres. And the way we have got this is that in this SQL editor, we have defined functions to check similarity, etc. Don't be worried about this for now. We are going to cover this. But currently, I just want you to understand the different varieties which can happen when we consider embedding models. How do you foresee vector databases to handle scalability issues? So in my understanding, vector databases are just wrappers on top of indexing, right? What is so special about vector databases like Pinecone or VV8 or Chrome? What's so special about it? The main thing which it boils down to is how they are doing indexing, right? How they are doing indexing. So as long as there are advances in indexing methods, vector databases will also keep getting better and better. But the real question should not be whether vector databases will solve the scalable needs. The real question should be, let's say if we have 1 billion queries, can someone come up with an indexing method which is fast enough for those queries? So right now I have talked about so many things, right? I have talked about, first I have talked about PyTorch. First, I've talked about PyTorch. That's by default you should go ahead with. And FAISS without even, if your problem is small, PyTorch plus FAISS will solve many of the issues for you. If you're building industrial level problems, instead of blindly thinking about a vector database like Pinecone or Milvus or VV8, Qdrant or Chroma, try to think of PGVector plus Postgres. And it might be useful if you already have data in Postgres, then definitely this is the option which you should go ahead with. But not many people know this actually. Everyone blindly uses vector databases. And I don't know why. I know they are good, they are private players, they are fast and they have indexing methods, but I have seen very less amount of material discussing indexing in particular. This is what we should ideally be discussing, I believe. Graph database, is it supported? I'm not sure actually if graph database is supported by Postgres. I understood that vector embeddings can be stored in same database. So let's say I give a natural language prompt. That's a good question actually. If you give a prompt, that is not embedded in that database. That is, the pipeline is like this, right? You have, let's say you have this table. You have this table where embeddings are there. The pipeline which we will also build today is something like this. You have a query. When a query comes, it is dynamically converted into a vector through an OpenAI API or open source model, let's say. So this is done during runtime. And then this vector we see which of these embeddings does it lie the closest to. So the query embedding is not stored in the database. The query embedding is calculated during runtime. In this table, I have just mentioned the comparison between Pinecone, Qdrant, VV8, Milvus, Chroma, Postgres, etc. I will be sharing all these notes with you, but I, while explaining, I've covered most of these points. The main thing is SQL support. SQL support is only there in these two Postgres option basically. And the other points I've already showed you. This is present in the drive link, by the way. In the drive link, if you go to Supabase SQL editor, what I'm showing you right now is present in that drive link. If someone does not have this drive link, let me share it with you now. In industry, if customers are already using some RDBMS, they are not fine managing another database like, yeah, then we can, uh, it depends, but I think now many are relational database providers will start to provide vector support, I think. How history will be maintained? History, there is a whole separate section for that. In context engineering, history is also an important concern, but I'll not go into that right now in the interest of time. We need same embedding model as previous, right? During query vectorization. Yeah. In query vectorization, we'll use same embedding model, or you can use, it depends actually, but there is no reason to use different embeddings really. Now with all this discussion, we can actually move to code and finish the embedding part. Okay, so until here, I think everyone has finished running. Just scroll down below. In the next part, what we have to do is that we have to just convert our embeddings into tensors. So if you access every embedding now, it will be a tensor, right? Has everyone reached until this point? Can you mention yes in the chat if you finished until here? So here we are loading the sentence transformer for one more time. It's not really needed, but now our embedding model is fully ready. I'm waiting for you to reach this point. Okay. Embedding model is now ready. And we have every embedding which is stored as a tensor. Next step, what we have to do is part number 5, which is the retrieval step R of RAG. So in this step, what we are doing is something which we already have been implicitly discussing. In this step, what will happen is that, let's say when a query comes, and that query is something like what are water soluble vitamins, that query will be converted into an embedding using the same model which we have. And then we are going to find the cosine similarity between the query vector and all of our embedding vectors. And we are going to return the embeddings with the highest cosine similarity. So this is the retrieval of the retrieval augmented generation step. So now when I'm going to go to code, I'm going to show you that, let's say we have a query like macronutrients function. We are going to embed the query. And then what we are going to do is that we are just going to use this function called dot score, which calculates the dot product between query embeddings and my embedding, all my embedding vectors. And then we take the top 5. We take the entries with the maximum score. And then we retrieve, then we print out the chunks, right, which have the maximum score. This pipeline, I hope it is intuitive to all of you, because now we are going to do this in code. So if you scroll down, you will see that this is my query. I am converting it into an embedding vector. And what is util, you might be thinking. So util is just from sentence transformer. It provides this util. I'm going to do util.dot score, my query embedding, and all of my embeddings really. So let me run this. So now you have 1680 embeddings, right? And you see within a fraction of a second, within 0.02 seconds, I found the dot product between my query and all my embeddings. That's extremely quick. And just for a random check, if we have 16800 embeddings, then let us see how much time it might take. If you have 16800 embeddings, then also it takes only 0.00064 seconds. And here we are not using any vector database. We are not using PGVector or Supabase or Postgres also. Just storing our embedding in torch.tensor makes it extremely quick. And next, what we are going to do is that we are just going to return the chunks. So we have this wrap text function, which returns the chunks which have the highest similarity score. So I'm going to run this right now, and you will see the chunks which have the highest similarity score to the query. If the query is macronutrient functions, these are my chunks with the highest similarity score. So this comes on page number 5, etc. Nutrients that are needed in large amounts are called macronutrients. And what we can actually do is check whether this is correct or not. So here I am getting the maximum score on page number 5, right? This chunk on page number 5. Let me actually see what's there on page number 5. So if you print this, and you will see page number 5 exactly has the same paragraph which we have retrieved. Nutrients that are needed in large amounts are called macronutrients. And we can check this here also. Go to page number 5 here. This, see what it says, page number 5, right? At the bottom. And we are getting nutrients that are needed in large amounts are called macronutrients. That is exactly what our model has also retrieved. So we say that the chunk which has the maximum similarity to the given question is on page number 5, and it has a score of 0.6926. Now there is another chunk which has been, second chunk also which has been retrieved. That is on page number 8. The third chunk is on page number 4. So let's see the chunk on page number 8 actually. There must be something. Yeah, so the chunk on page number 8 is actually getting confused between micronutrients and macronutrients, I think. Because here we are talking about micronutrients. So this is what I meant by embedding models being good, right? Since we used a small embedding models, maybe it's thinking that macronutrients and micronutrients are the same thing, which is not the case really. But until now, we have got a sanity check that the responses which we have got are actually matching with the exact text. Did we do any query transformation? We have not done any query transformation so far, Sanjeev. Query transformation, the scenarios in which query transformation needs to be done are a bit more complex. So let's say there is something called query routing engine, where if a query needs to be routed to a specific LLM during runtime, that whole engine is required. But we are considering a very simple case here, where the query transformation is not needed. But I will point out to some references where you can read about query transformation. I got page number 4, 7, and 11. Amit is saying. You can check, Amit, what are the responses which you get on page number 4. So how many of you got these responses like page number 5, for example? Can you mention in the chat? Okay, so good sanity check. Is everyone clear until this point? Are we okay to proceed further? Okay, so before we come to the next step, which is actually uh, having the generation pipeline attached, here there is a simple difference which I've mentioned between dot product and cosine similarity. I hope all of you are aware of this difference. When you take dot product, you also consider magnitude into account. But when you consider cosine similarity, it only takes angles into account. And it divides by magnitude. So everything is really normalized. The main function which we are going to define at the end of this part. So this is now the end of our part, which is part 5, the retrieval. The main function which we are going to define at the end of this part is retrieve relevant sources. In this, we are just putting in a functional format what we have seen before. So this retrieve relevant sources, what it will do is that it will take a query and it will take our embeddings matrix, which we have stored in PyTorch. It will take our embedding model. It will take the number of matched queries we have to return. And it will do the exact same thing. So it encodes the query into an embedding first. Then it calculates the dot product between the query embedding and all of my embeddings. And then I print the top results over here. I print the score, I print the page number, and I also print the text. So this print wrapped actually prints text in this kind of a manner, like wrapped text. So this is the main function which we define at the end of part 6, which is the retrieval step. And now you can actually go ahead and check whether this function is working or not. So let's say I have this thing called symptoms of Pellagra. I run this and I get the scores and indices of the top 5 chunks. And then I print the top results. And here you see niacin deficiency is commonly known as pellagra, and the symptoms include fatigue, decreased appetite, and indigestion. So this is a very good answer. Let's see where this is present in the document. If I control C and if I do control V here, niacin. So what's the exact text actually? Niacin deficiency. Yeah, this part. See, niacin deficiency is commonly known as pellagra, and the symptoms include fatigue, decreased appetite, and indigestion. That's the exact same answer which we have got over here, and the page number is 565. So when you add 42 to this will be 607. So 565, and here it is 607. So page numbers are also being printed correctly. All right, so now we are ready to come to, so retrieval part is done. So part 5, which is retrieval, is done. Now we are actually coming to part number 6, which is the generation of RAG. Let me see if there are any questions in the chat meanwhile. Audio is breaking. Okay. Can you try a query across different chunks? Yes, Dishant, you can feel free to explore that after this lecture is over. Now that this code file is there, you can analyze your chunks and try a query which is kind of confusing across chunks. Apart from cosine similarity, which is generally used for text similarity, can we use any other similarity? L2 distance is one similarity metric which might be used, but when you have meanings associated with vectors in higher dimensional spaces, cosine similarity is the most preferred option. I have not used any other similarity metric for RAG related applications, especially. So now we come to part number 6. Now only 2 more parts are remaining. Part 6, which is the generation of RAG, and part number 7, which is augmenting generation with retrieval. So again, we are going to take a small break over here for maybe 3 to 4 minutes. And then I'll come back around 9:45, where we'll cover generation and we'll cover retrieval augmented generation, the whole pipeline. And then after that, we have to look at evaluation, and we have to look at actually building the whole production-based pipeline in Postgres. I actually don't know how much time it will take, because it's difficult to predict. If there are more questions, it might take more time. But it depends on you, as always. Yesterday also I mentioned that if you have other commitments, I'll share the recordings after the lecture is over anyways. But I want to make this as comprehensive as possible so that later all of you can refer to it. Okay, I'll come back after 2 to 3 minutes. All right, everyone. So let's continue now. We have finished 5 parts in our pipeline so far. So part number 1 is, uh, yeah. So part number 1 is essentially intro to what we are building. Then we had document pre-processing. Then we had chunking. Then we had embedding, and then we finished retrieval. Now only the last step of this puzzle is remaining to be done. So far, let me show you what all we have covered. We have covered processing text into chunks. So chunking is done, embedding is done. We have stored our embeddings. And actually retrieval part is also done. So if some query is asked, we know that some chunks are going to be retrieved. So these relevant passages are done. And that was covered in this last function which we saw. This last function is the most important to remember. The last function is called retrieve relevant passages or retrieve relevant resources. Now we come to the last part, which is language models. And yesterday we used OpenAI API key. Today, and again here the engineering choice which I want to mention here is that there are two choices for an engineer basically. The same choices when you deal with LLMs. You can use an open source LLM or you can use a closed source LLM. So the main question which you want to ask is that, do I want to run it locally? Is privacy going to be important for me? Then you have to use open source models and you can build a fully local RAG pipeline, which we are going to do right now. And the second is a much simpler thing where if you absolutely want the best performance, then you can use an API call to some of the best models. So remember that here again, there is a choice to be made. If every information needs to be present on your local server, go with open source models. But if you want state of the art performance and if privacy is not a concern, you're willing to make API calls, you can attach an LLM, which is a closed source LLM also. What we are going to do is that we are going to use this model today, which is Gamma 7B IT from Hugging Face. Now, before we use this model, can every one of you go to this link? By default, I think you will not have access to this link. Where does re-ranking fit here? So Jaydeep, re-ranking fits not in RAG really, but in semantic search. If you are doing semantic search like how Microsoft Bing or how Google does it now, they first they have a keyword pipeline and they have re-ranking pipeline on top of that so that the semantic search becomes easier. The underlying framework is the same, but it's those two things which are linked together. Can everyone go to this link? You will see something like gated model, but you have to click on provide permission or something to get access to this model. Once you do that, the second thing which you will need is that you have to go to access tokens. First, I need to again confirm my identity over here. Valid password. I can't seem to remember my password here, but I've already saved my token. So I'm going to use that for others. You can create a write token on Hugging Face and just copy that API key. So for example, for me, it will be something like HF underscore, okay? Has everyone actually copied this? Can you let me know? You have access, right? Where do we get the token? So Amit, what you have to do is that on the top right, you have to go and click on access tokens. And then you will need to confirm your identity. So if you remember your password, unlike me, I seem to have forgotten my password over here, which I'll need to check. But if you remember your password, when you click on confirm, you will be taken to a page which will look something like this. Um, yeah, it will look something like this. So you have to create a write token, though, not a read token. You have to create a write token and then click on generate a token. Yeah, Mayank has shared his screen. So, Mayank has shared a screenshot. So in that screenshot, if you see on the chat, you have to click on the right and then click on generate a token and then copy whatever you see. Once that is done, what you have to do is that let's go to code right now. And for all of you, you can check your available GPU memory. For me, it's 15 GB. Then scroll down below. And for 15 GB, usually you will be downgraded to a Gamma 2 billion IT. So let me search this. How much GPU memory is showing for all of you? Because if you are on A100 or something, it might show 40 GB. Then you can use the 7 billion model also. But if you are on T4 GPU, then we have to use this quantized 2 billion model. Where does re-ranking fit here? So re-ranking, I think I already answered this question. Re-ranking is more related to the semantic search pipeline, not too much in the RAG, where in the semantic search you do a keyword search which is fast and then do re-ranking only on the keywords. But the underlying procedure is exactly the same to what we are seeing in the RAG. So if all of you have a 15 GB memory, right, you will only have access to 7 billion, not the you'll have access to 2 billion, not the 7 billion. So again, you'll need to go here and click on grant access. So that is done. So this piece of code will automatically set your model ID to an appropriate model based on the memory. So scroll down below and here is where you need to put your Hugging Face token. Ideally, this should not be exposed, but this is the fastest way of doing it in code right now. So just paste your Hugging Face token like I have done here. And then what you can do is that you can download the model. So the model download begins at this point, right? And remember the fact that we are not using a very large model here. We are using a relatively smaller model. So your answers need to be judged accordingly, right? It's a very small model actually. It's a 2 billion model. Whereas if you made that API call to GPT, it would be 1 trillion model. So definitely your answers will be good. But this is just so that you get a feel of running an entire RAG pipeline locally. And open source LLMs quantization will be the future, I think, of language modeling. So it's also good for you to learn about quantization. Here we are doing quantization, by the way. We are using this package called bits and bytes, so that the model is quantized and things can be run in a much faster manner. You're trying to access a gated repo. So for this, you will need to go to that you'll need to go to Hugging Face and you'll need to give access actually. So Sanket, if you are facing this issue of gated issue, just go to this link on your Hugging Face account, go to this link and you will have to give grant access to this model. There will be something there which shows that you don't have access or something. You just have to click on grant access. Then you will be given access. So my access got granted almost immediately. What about others? Did you get access granted to this model? Yes. So if others also have got access, both of you should also get your access resolved. What base did it take? So it took the gamma model as its base and then it quantized it. So the gamma 2 billion base model, that's the base model which it took. Gamma 2 billion instruction tuned base model and it quantized. So by quantization, the simple thing you can think about it is if you have a model with 2 billion parameters, right? Each parameter will be represented as 16-bit floating point typically. That takes memory, that takes space. So what if you can represent that same parameter as 4-bit or 8-bit or even 1-bit as Microsoft has shown recently? You still don't lose that much performance, but you save a lot on computational time. That's called quantization. So along with parallelization, quantization is the only way I think to make models faster. See, chip size is not getting any smaller, right? The Moore's law is almost dead. The only way things get faster after this point is quantization and parallelization, at least according to me. Where to ask access? So there itself, if you don't have access, it will be written that you don't have access to this on that same link which you have shared, Manoj. But once you get access, then you can print this LLM model. So and you can print the number of model parameters. So I'm going to stop over here right now and ask how many of you have reached this stage where you can see this number of parameters printed for the model, and the model is now downloaded locally for you. In process, yes. Okay, good. So getting downloaded. Okay, it won't take too much time. So this acknowledge license, yeah, that's the main thing. As Sandeep has mentioned, if you click on acknowledge license, you will directly get access to this model. And you will see how much memory this model takes. It's around 5 GB, and you have access to around 15 GB on T4 GPU. So you should be good over here. Now what we can do is that we can just test whether our model is generating text or not. Here we are not combining the retrieval part at all. This is just generation, where we have downloaded our local model and we are asking it random questions, uh, and we are giving the prompt in a particular template. And here we can see that after the model input is given, the model will generate some outputs. This will take some time because we are on a T4 GPU, but the model generates some outputs which you can decode back into text. So if the question is what are macronutrients and what roles do they play, the model gives an answer by itself. This is a sign that our local LLM is now working and ready to go, right? So if you print the input text and the output text, you will see if you are using a local LLM for the first time, this will be a great experience for you because now on your Google Colab, you have mentioned the input, you have mentioned the output, and you have downloaded an open source model to get a prompt, to get a result rather. So Madhusudan has got an error. One or more modules is configured to be mapped to disk. Disk offload is not supported for models. I'm not sure why this error. Are you running on runpod? Because this error sometimes shows up on the runpod. Yeah, that's the main reason I think. So until now, we have not routed our model to our document at all. We are just generating answers, right? So if you take the analogy back to the open book exam analogy, which we saw, until now, we are just generating answers from our own mind. We are just generating answers from our own mind. We have not retrieved anything. We just want to check whether the generation part is working or not. How many of you have finished until this point and uh, you are now sure that your generation part is working? Yes. What about others? In process. Okay. Now that the generation part is working, now we are at the last stage actually. The last stage for us is augmenting the generation with retrieval. This is where everything comes together, right? You remember we had written a function to retrieve the most relevant items. Those relevant passages will now be augmented with our query and will be passed to our LLM. In this case, that's going to be a gamma. And then we will get an answer. And hopefully that answer will be grounded in our document. How do we know it's grounded? Because the relevant passages which are going to be passed are from our document itself. We are passing the top relevant document or top 5 from our document itself. Along with the query, these relevant, so the whole pipeline looks something like this. You make a query, you retrieve the relevant sources, and then you augment the prompt with the retrieved context. So in the code, you will see there is something called prompt formatter. This is one of the most important steps. And this is again why we had the lecture on prompt engineering in the week before this, right? Because check what we have done here. We have told the LLM to augment the query with the context from the context items. And where will the context items come from? They'll come from the sentence chunks, which we will pass from our retrieved chunks. So the retrieved chunks will be given into context. We already have the base prompt. And on top of the base prompt, we are also saying that extract relevant passages from the context and add it to the base prompt. So the base prompt is now augmented with this context. This is where the whole RAG step actually happens. This is the augmented part. Why is it called retrieval augmented generation is because the prompt is augmented with the context. And the query is still passed the way we would pass an usual query, but the prompt is now augmented with the context and it's passed along with the context. So we pass the augmented prompt to the LLM and then we get grounded outputs. That's the last piece of the puzzle. So here what we are doing is that we are just making a query list and we are generating a random question from this query list. And then this is the main part where I want you to pay close attention. This is the prompt formatter which we have written. And where will the prompt formatter get the context from? The prompt formatter will get the context items from this function. So we will first call this function. This one right here. We are going to call this retrieve relevant passages, retrieve relevant. Whenever a query is passed, we'll call the retrieve relevant sources and we will get the top chunks, right? These top chunks, then we will pass to our prompt. These top chunks are going to be passed to the prompt formatter right over here as context items. Then the prompt formatter will have these context items. It will create the context and augment the query along with the context. So run this right now. And then let's just check whether our prompt is getting augmented or not. So the query is, how does saliva help with the digestion, right? And here is our normal base prompt. And this part which comes, that's getting augmented because of our RAG part. These are the retrieved chunks. So this whole prompt which you see right now for this question, if we did not do RAG, only this prompt will be passed to the LLM. But now that we have done RAG, all of these things you can already make out from this University of Hawaii, which we should have deleted by the way. But anyways, all of these context is coming right from our book. So that's rooted context. We can check this actually. Digestion and absorption of carbohydrates. If you go and if you paste, yeah, it's this chapter. It's this chapter where the question is asked about saliva, right? That's why chunks have been retrieved from this chapter which are related to saliva. And our prompt is augmented. So this kind of shows that our augmentation is working and we are good to go ahead. And the last thing is where we pass this prompt. Now the augmented prompt we pass to our LLM just like we did before. The augmented prompt is passed to an LLM and the query is, how does saliva help with digestion? The answer is the passage does not explicitly discuss how saliva helps with digestion, so I cannot answer this question from provided context. Now this might have happened because this, if you see, is not directly, the passages which are retrieved are not directly related to how saliva helps digestion. So this again indicates that our RAG system is not entirely robust. We need to make maybe chunking more, or we need to do more semantic level chunking, etc. Let's check for some other query. So if the query is now describe the process of digestion and absorption, here also we get some prompt. Let's pass this. Yeah, see now the answers are good. Now we know that all of these answers which are given by the LLM are based on my book, are based on my grounded text which I've mentioned because it has been passed in the prompt. When the LLM thinks that the context does not have too much information, then it actually says that the context does not have too much information. We can even add that here, that if you don't have enough context, you can mention that I could not extract enough context. And that's also fine. That is actually a sign that we need to improve our RAG system more. But for this question which has been asked, describe the process of digestion and absorption of nutrients in the human body. This is the context which has been retrieved from our book, and this is the answer which has been generated by our local LLM, which is now running on our GPU. Remember, for this local LLM, we are not passing the data anywhere else. The data stays within our server. We are not making an API call at all. So this is quite cool that with just a 2 billion parameter model, we are able to generate answers which are coherent. Because of course you will generate good answers with chat GPT, right? It has 1 trillion parameters, but we are on a T4 GPU right now, which is a free GPU from Google Colab. And still we have got the entire RAG pipeline to work from scratch. Let's see if there are any questions. This is, yeah, ultimately the RAG, it cannot be called as a few shot learning actually, because in few shot learning, we provide an example that this is few shot learning is different than RAG. Few shot learning does not require you to maintain a knowledge base. What is the underlying reason that the model is able to generate responses based on the context? Yeah, so in this case, model is instruction fine-tuned, right? So it knows how to follow instructions. How do I know it's instruction fine-tuned? Because you are using a Gamma 2B IT model. IT means instruction fine-tuned. If you check the model which you are using, uh, yeah, it's Gamma 2 billion IT for us. So it's an instruction fine-tuned model. And remember that these models are trained to follow instructions, which has been clearly mentioned in our prompt because of the augmentation. So once you understand the retrieval process, the whole thing which comes after this point is prompt engineering. How well you are writing your prompt, how well you are instructing the model to pay attention to the context, when it should pay attention to the context, when it should not pay attention to the context. That is going to be extremely crucial. So this is the entire RAG pipeline assembled end to end, where this is entirely built on local GPU. And what you can do towards the end is that you can put this in one function, which is called ask, which just takes in a query. Uh, it gets the context and it also responds with the answer and the embeddings. So this ask function, which I've defined towards the end, what it does is that it puts all of this thing together. It gets the query, what are my macronutrients? It gets the answer, and it also shows the, so remember for this question, we had already identified the retrieved chunks. Here are the retrieved chunks. So these are the chunks. If the question is what are the macronutrients and what role do they play in the human body, what happens is that for this query, we first get retrieved chunks, which are these. Macronutrients are needed in large, nutrients that are needed in large amounts are called macronutrients. And they are on page number 5, which we have already seen. This. So now this is the chunk which has been retrieved. It has been augmented to the prompt. And then here's the answer which our RAG system has given us based on this augmented prompt. And then here I have also printed the embeddings, etc. So many things have been printed over here, but the most important things are the context items which are passed to the prompt and then the final answer really. So this is an indication that our RAG pipeline is working. Whenever we ask a question, it's collecting the right context and then it's providing the answer. So here also we did a very simple RAG system here, right? We only did fixed size chunking. Now towards the end, if you see that some answers are not good or some answers can be improved, I've already shown you how to go back and change the chunking strategy which you can use. You can use semantic chunking, you can structure based on pages. In fact, what I did is I have run this entire code on structural chunking where every page is a chunk. So remember yesterday we kind of had a modification where instead of 10 sentences, we had each page as a chunk. This is what I exactly did in this RAG pipeline. So I kept the whole thing same, but if you remember yesterday, we had identified chapter names wherever this University of Hawaii appears. So what we did yesterday is that Whenever a new chapter starts, it's this thing which appears, right? So we created a chunk there and we ended the chunk at the end of the paragraph. So here the issue which happened for me, which is also a good thing for all of you to illustrate, is that take a look at the answers which I get, or I'll show you the answer which I get. This is the answer which I get. Why do you think that is? Can someone tell me? This is the answer which I get for the exact same RAG pipeline done with structural chunking and using the same LLM which I just shown you. Context overload, that's the correct answer. So the reason I got difficult answers here is I used a model which had very low context size. So here, check what's been mentioned here. The current text generation will exceed the model's predefined maximum length 8192. I think the issue is because the entire thing is being passed to the model context and the model does not know what to deal with it or how to deal with it, because we are using a very small model in this case also. I also did semantic chunking, by the way, and semantic chunking gave me good results, although it led to a huge number of chunks. So I've ran the entire pipeline now using structural chunking as well as semantic chunking. And I will share these Google Colab notebooks with all of you after this class is done, so that you can mimic the same pipeline which I've done now, but instead of uh, fixed chunking, you can do structural chunking or semantic chunking as well. Let me see if there are any questions in the chat. How is the agentic RAG different from this RAG? So in agentic RAG, right, the only difference is that we are going to learn about agents in this class later, but agents have access to tools, right? Usually these tools are a web scraping engine or a code writer, etc. If one of these tools is a vector database, one of these tools can be a vector database, then the agent system becomes an agentic RAG system, where based on the question, the agent can decide whether it wants to use this vector database or not. That's agentic RAG essentially. Can we discuss a little bit about multimodal RAG? I am going to do that at the end of the class when we do the production level RAG. How was the output from semantic chunking? I would not say it was better, but it was decent. So for example, yeah, I got outputs which were very relevant to the paragraphs, but the context which was passed in was very small because the chunk size was very less. But answers were good. Answers were not as bad as structural chunking, but I would not say they were better than fixed size chunking, mostly because, as we saw yesterday, if you remember, um, semantic chunking has some disadvantages. Its average chunk size is very less and its number of chunks are huge. Instead of Gamma, can we use any other LLM? Now, one thing which I would want to mention to all of you, now that you have asked this question, is that the way I've designed this notebook is that it's completely modular, which means that we discussed several things, right? We discussed chunking strategies, we discussed embedding models, we discussed open source plus closed source LLM, and at the start, we also saw file ingestion. Now, and I have given you enough information about the engineering trade-offs at all of these places. So you can feel free to explore everything in this single notebook. You can very easily make an API call to a closed source LLM. You can use other open source LLM like Qwen to check whether they are doing better or not. You can explore other embedding models on this MTEB leaderboard. You can take more complex embedding models to see if they are doing better or not. You can try doing recursive chunking. You can try a mix of structural plus recursive chunking. You can try dockling over here. So you remember at the start that I mentioned that the way I've structured this bootcamp is foundations plus practicals plus research, right? This last part is what all of you now need to do after attending this workshop. So after this workshop, you will have the knowledge, but that still does not guarantee you will be able to do new things on your own. The only way you will be able to do that is if you get stuck. So if you are exploring some chunking strategy and if you get bad responses, that's an indication that you have gotten stuck. What you do at the moment will determine how you are as a researcher, right? If you just give up, uh, then that won't teach you anything. But if you try to overcome that challenge yourself, you will become better and better as an engineer as well as a researcher. Another thing you can explore is vector indexes like Pinecone. Uh, the tutorial on their pages are just very easy, quick start tutorials, and they're identical across Pinecone, Milvus, Qdrant, and Chroma DB. You can just use one of them, integrate it in our Google Colab notebook. It will be a very simple integration since the whole thing is modular. All these parts which I've mentioned are completely modular in nature. Is this workshop any? Yeah, the workshop is essentially part of a live course. It's the LLM production and deployment live course. Oh, I've received a message that my OpenAI API key is exposed somewhere. I was not aware of that. Let me check it. Oh yeah, it's exposed over here. Let me. Actually, we will need it just right now. That's why I've kept it. After going through this, I will delete it. But yeah, if all of you make simultaneous calls over here, the budget will get exhausted. So better to just. Okay, so now what we are doing, one last part is remaining in our end-to-end RAG pipeline, and that's evaluation. And the issue in industrial LLM implementation is that not many people talk about evaluation as much as they should have, because many people asked yesterday that how do we know whether a RAG pipeline is good or not? How do we know whether the chunking strategy is good or not, right? In fact, there is still some research being done on this area and nothing is quite foolproof yet. But there are some common standard practices of evaluation which I'm going to share with you right now. There is a very good paper called Evaluating Verifiability. There is a question in the chat that so this class is actually part of this our generative AI minor, the third course of our generative AI minor, which is LLM production and deployment. So if you see if you see the course content, we are right now here. All of these other things are remaining. But anyways, what I was mentioning was this paper called Evaluating Verifiability in Generative Search Engines. I think this was one foundational paper which gave a roadmap on evaluation in the RAG-based systems, right? Before that, there was no professional or no concrete roadmap, but they actually defined many metrics like citation precision, citation recall, etc. And now one of the most popular libraries which I'm going to discuss right now is this one called RAGAS. How many of you are aware of this? So if you go to this RAGAS, they have a famous GitHub repository. And the thing is, I don't actually like RAG evaluation libraries too much because in industry settings, we define the evaluation criteria ourselves. I've never used a RAG evaluation pipeline to define a criteria because in many cases, the evaluation depends on custom metrics. But there are some common patterns which I would like to mention and some common evaluation metrics actually. And some of these are context precision and context recall. So if you have dealt with classification, it's actually similar to classification precision and recall. So if you take a look at context precision, it measures the proportion of relevant chunks in the retrieved context. So if, for example, you have 10 chunks which have a similarity score higher than a threshold, but in the retrieved if you have 10 chunks in the ground truth you know are relevant, but in the retrieved chunks you have only 5, then that leads to a low context precision. Then another metric is called as context recall. So this measures how many of the relevant documents were successfully retrieved. There are many things like this, but if you think from an intuitive point of view, what are the parameters which you will consider intuitively? If we forget about libraries for a moment, what are the parameters you will consider intuitively? The first thing which I will at least consider is that, are my chunks actually relevant? Are my chunks relevant to my ground truth? That is the first thing which I will consider. Then second, okay, if my chunks are relevant, am I covering all the relevant chunks? So let's say if the chunks retrieved are only on page 2, but page 400 also has some relevant chunks. Am I covering all the relevant chunks or only a subset of the relevant chunks? That's the second question which I will ask. What is the other thing which you will ask? Yeah, whether write docs are retrieved for knowledge base, this we already considered. How is it decided if a chunk is relevant? So we need to maintain a ground truth. And this is extremely important. We need to make, so what we do in practice is that we make an Excel sheet actually. And that Excel sheet will have a list of 20 to 50 questions. That Excel sheet will have relevant passages which are actually correct. That Excel sheet will have relevant passages which are actually correct. And that Excel sheet will also have answers which are correct. Answers which are correct and related to my document. So this is my ground truth now. Based on this ground truth, I will actually evaluate whether my chunks are relevant or not, whether all the chunks are indeed retrieved or not, or only a fraction of the chunks are retrieved. So if you check the metrics which they have this context entities recall also, which gives the measure of recall of retrieved context based on number of entities present both in reference and retrieved context. So reference is the ground truth which we need to maintain. Even to use the RAGAS library, you need to maintain a ground truth of reference. Then response relevance, that is also very important. Measures how relevant a response is to the given input. So this you can do with simple cosine similarity, for example. But the way we typically do it is that we do it on intuition. If we get a problem from a client, right, and we know the relevant metrics which they are looking for, are the chunks relevant? Are all the chunks retrieved? Then are the answers correct or not? Are the answers actually grounded? Are the answers actually grounded or not? Are the answers actually specific or not? Specificity is also very important. Basically, how much of the information from the grounded document is used versus how much of it the LLM is generating on its own. How to generate ground truth data? So ground truth data definitely, I would say, generated manually. Many people generate ground truth data through LLMs, but I don't believe in that because LLMs already hallucinate. So if you want to reduce hallucinations, you are using a ground truth data from an entity which already hallucinates. That does not make sense, right? The best thing is to create your own set of ground truth data, and it does not take too much time compared to the amount of the whole evaluation pipeline depends on this table, right? Your recommendations to the client depend on the table. So how much, let's say you have spent X amount of effort in making this entire RAG pipeline, which we just showed, which is significant amount, and you don't spend any effort making this ground truth data. That's not a good thing to do because all your metrics will ultimately depend on how well constructed your ground truth data is. Now, the question is, how do we, there are some things which are very qualitative, right? Like how do we know how specific, let's if the answer is specific or not? For that, there are two things to do. You can use LLM as a judge or you can use human as a judge. Some things can be found out through simple cosine similarity. So for example, if you want to check whether the answer is relevant or not, you can convert the answer and your response to uh, embedding vectors and find the cosine similarity. That's fine. But there are some answers which are a bit qualitative. Like what if I want to check whether my answer is specific? For that, you can use LLM as a judge in this case. But mostly if human as a judge is there, it's better. So what we also typically do is that we LLM as a judge we do within our organization, and human as a judge we ask the client to do. So then they are also happy that way. They get the results and then their people can judge whether the answers are good or not. This is usually the best method because then the client is also in the loop and then their feedback is incorporated, right? Later you can pass this human feedback also into your knowledge base and keep on continuously improving the knowledge base. Many things can be done after this point, but if the client is involved as a human in the loop for your evaluation, that's the best thing to do. What is relevant in ground truth data? So relevant is essentially if I ask question about macronutrients, right? I know this passage is relevant. So I'll copy this passage and I will paste it in my Excel sheet. So some amount of human intervention, but if the document is huge, then of course you need LLMs to look at to create this ground truth. But again, human in the loop has to be there somewhere to at least verify whether what the human has done is what the LLM has done is correct or not. If you have 10,000 documents, you cannot sit down and construct ground truth alone or individually as a human. Then you can bring a larger LLM to create that ground truth, but have a human in the loop to verify it for sure. So what we have done in this last section of the code is the final step of our pipeline, which is evaluation. And here I have actually installed the RAGAS library. So this is the RAGAS library from GitHub so that we don't have to define metrics manually in this case. We can quickly get some of the metrics which they themselves have defined. Now that this package is installed, you can actually import metrics such as context precision, recall, answer relevancy, faithfulness, etc. And for these questions, I have actually created ground truths. See, even for RAGAS to work, you need ground truths. I have not spent too much time creating this ground truth. I have just taken some important sentences from the text and created these ground truths for my evaluation questions. And then I'm generating my RAG answers. And then finally, I'm just doing the evaluation using the RAGAS library. Now, you will be able to follow along with this tutorial if you have your OpenAI API key, right? So if you please use your API key because otherwise my budget will get. So now I've utilized this. So by default, what RAGAS will do is that it will use models from OpenAI to judge these scores. So see right now, I have 5 questions and I have five questions and I have 5 metrics within each question. So that is why there are 25 evaluations which are to be done. And we can actually print out the individual performance. So you can see that for each question, I can get my context precision scores. I can get my context recall scores. I can get my answer relevancy. I can get my faithfulness. And I can also get context entity recall, let's say. And you can print overall average scores. So now let's say if you want to evaluate a chunking strategy, just get these overall average scores and you will see that for chunking strategy A, my answer relevance is poor, my faithfulness is poor, my context entity recall is poor. Then I will run chunking strategy B. So ideally what is done is you assemble this entire end-to-end RAG pipeline, you create a grid of whatever hyperparameters you want to test, the different chunking strategies, the different embedding models, you run them end to end. And for all the different hyperparameters, you collect this final table of performance essentially. And then finally, you will want to go ahead with that strategy, which gives you good performance. For this to work, you need to have ground truth, which has huge amount of information, not just 5 things which I've shown you right now. Your ground truth should be extremely detailed. It should be comprehensive so that you can actually take a call based on these results that, okay, structural chunking is not giving a good relevancy, whereas fixed chunking, whereas recursive chunking seems to do good on all the metrics. So I'll go ahead with recursive chunking. That's a call which you can take. So this is another evaluation step which you can do to determine what hyperparameter to use. This along with the chunking strategies, you can get a statistical evaluation earlier itself. But overall, you will get an evaluation only when you run the end-to-end RAG pipeline. And if you want to automate this further, you can also, if you want to generate a summary for each hyperparameter you tested. So let's say if you have a system in your company where engineer, manager, and then a person who deals with the client, these reports can be automatically generated so that they get passed on to the manager and then to the client, let's say. So this whole thing can be automated really. The end-to-end code which I've assembled, which I've shown right now, this whole code can be wrapped around in a for loop and you can try out various things. What are the various things you can try out? You can try out chunking strategies, embedding models, different types of LLMs, different vector indices. And towards the end, you can just get the different evaluation metrics like what I've got here. And then you can zero down on the thing which works the best. That's how usually it is done in industrial projects. But companies want to make everything in a day because they think ChatGPT. So this depends, right? Because if you have good clients who actually know what they are talking about, they don't think like this. Many people who are really into the field understand the limitations of GPT, understand hallucinations, know what vibe coding is, and they are completely on board. The best thing you can find is a company who understands different models, right? Yeah. But honestly, we have had good experiences dealing with professional clients so far. Can we train a classifier to suggest the best chunking strategy? That's a good suggestion. But you still need to wrap that whole thing in this end-to-end pipeline, right? Because the chunking strategy will depend on the final result of your RAG pipeline. So if you want to, so let's say if you have an end-to-end RAG pipeline, why do you want to convert that into a classifier again? You can just do hyperparameter testing or grid testing and find the best strategies. Does anyone have any doubt or any question in this? So someone asked a question of faithfulness, right? Faithfulness is actually how factually consistent a response is with the retrieved context. So this is also an important metric which can be used, and you can again use an LLM to judge this metric. So this covers the last part of our end-to-end RAG pipeline. We have now done 10 parts together. Total, it has now yesterday 3.5 hours plus today 2.5. So total, it has taken 6 hours for us to cover this entire RAG pipeline. But I hope all of you are now familiar with all the parts. So let me quickly recap. First, we did this foundationals, practicals, and research approach. Research approach, I have suggested to you to try out various things towards the end. Then we went into document pre-processing part 2, where there are options such as Tesseract, Dockling, PyMu PDF. Then we went to part 3, where the trade-offs are between fixed size, semantic, recursive, structural, LLM chunking. Then we went to part 4, which is embedding the text chunks. So honestly, chunking and embedding are the most crucial parts. In embedding, I hope you understand the nuances of different embedding choices. Start with PyTorch plus FAISS, then and only then if the number of database vectors are huge, billions, think of a vector database management platform. If you are already having your database in RDBMS like Postgres, think of PGVector, because then you have two advantages. Both all your databases will be in one place and you can use SQL, like the tea kettle principle which we discussed. If you are given a new problem, try to find ways to solve it using something you have done previously. Then we came to part 5, which is the retrieval pipeline. You get the query, convert it into an embedding. You convert the chunks also into an embedding and find those chunks which have the highest cosine similarity between the query and the embedding vector. Why don't we use a simple, why do we care more about angles than the magnitude here? Remember, cosine similarity only cares about angles. Magnitude is normalized because magnitude is often a noisy metric. It can carry other things which might pollute the similarity, right? So keep this into mind. This is sometimes asked in interviews. Then we return the embeddings with the highest cosine similarity. Part number 6 is the generation part where we try open source versus closed source. Here we did open source. Part 7 is where the prompt is actually augmented with the retrieved items in this step. Here prompt engineering again plays a very crucial role. And last part 8 is the assembling the whole RAG pipeline. Part 9 is I have told you the research mindset of what all to try next. And part 10 is actually part 10 is as important as part 1 to 9 combined. Although we have spent less amount of time on it, but part 10 is extremely important to assemble a good ground truth data to determine good metrics. I've already suggested some metrics which are useful, like faithfulness is a good one, context recall, context precision, and context entities recall. So these 10 steps are the end-to-end RAG pipeline, and then to evaluate which of the hyperparameters work best, usually you assemble the whole pipeline and run a for loop like in a grid testing manner, and then see which combination actually works the best. Okay, so updating RAG pipeline is again the issue of drift, right? So just like there is a issue of data drift in ML models, context can also drift. So that's the whole separate thing. We need to keep on updating the RAG pipeline at frequent intervals to make sure that it's still working. So if a RAG pipeline becomes static for multiple months and new documents are being ingested each time, there may be drift. Can you use Streamlit for UI? Sure, you can use Streamlit, you can use Gradio. Those are good UI tools to use for initial demonstrations at least. Can you mention strategies for images and tables? So Gaurav, most of the things which we have covered so far have mentioned images and tables, right? Because dockling will take care of images and tables for sure. Many embedding models which I showed you were multimodal embeddings. They will also take care of images. So as long as dockling parses your tables into a good format, you are good to go. Dockling can also parse your images. So at the source itself, if you use an extractor which deals with tables and images, later you can use a multimodal embedding model to deal with those. So the whole pipeline which we have assembled is fully customizable to text, images, as well as tables. There is a question, do we have to store images in vector database? Good question. In fact, I'm going to show you how to do that. Now when we are going to next, now what we are going to do in the last part of this workshop is we are going to build an application out of this. So essentially what we are going to do, this entire pipeline, we are going to convert it into a front end and a back end type of a system. So in the next part, what we are going to do is that we are going to start with Supabase. We are going to write an SQL script over here which retrieves. So first we are going to write an SQL script which creates the table which I showed you. That table will have chunks, embedding everything in one place. And we are also going to write functions which find cosine similarity, which retrieve the most relevant chunks. So functions to retrieve relevant chunks. Okay. This is going to be our database. Then what we are going to do is that we are going to go to VS Code. We are going to write a script called ingest.py, which will ingest our document. It will convert it into chunks and it will upload those chunks to the Supabase table. And we are going to use OpenAI embedding models over here. Because I have already showed you how to use open source models. Now let me show you how to use closed source models. We are going to use OpenAI embedding models over here to create these chunks, upload to Supabase. Then what we are going to do in VS Code is that we are going to uh, write a backend API call where don't get too intimidated by this. We are going to do it in a very simple manner. When a user asks a question, when the user asks a question, this question is going to get converted into an embedding. This embedding will be converted, this embedding will be matched to our chunks table. So remember this match function we are going to define over here. So this embedding will be matched with our chunks table and then the retrieved relevant informations will be retrieved. These informations will be passed to the prompt. And then we'll see an answer on our front end. We are going to assemble this simple workflow and then we are going to kind of put this whole thing into Lovable and let's see what Lovable gives us. So let me repeat what we are doing. First, we are going to go to Supabase, create an SQL editor function, which will create a chunks table where our vector embeddings will also be there. Here we will also write functions to retrieve relevant chunks. Then in VS Code, we'll first write a script to download our file. We'll write a script to download our PDF file, make it into chunks, we'll upload these chunks to Supabase. And then in VS Code, we'll write a backend API, which user asks a question. It's converted into an embedding, which is matched with the chunks. We retrieve some answers that's added to the prompt, and then we show the responses on the front end. This will give a very rudimentary front end API. We are going to put this whole thing into Lovable and let's see what Lovable gives us. Is this overall workflow clear to everyone? Can you mention it? What we are planning to do, is this overall workflow clear? I will explain it once more. So when we are going to actually use these tools, I will go through it once more. So don't worry about it. Right now, just think about Supabase, VS Code, backend API, just three things. And then we are going to put all of this into Lovable. Haven't used Lovable, no problem. You just we are going to use it as a prompt tool basically. I'll show you how to do all of this. So this is what we are going to do next in the last section. But before that, again, let's take a small break so that your mind is refreshed for this last section in which we are going to convert this whole pipeline into a web app. And I don't want to show an app in Streamlit or Gradio. I want to show how we actually do it in production level. So we have actually built an app in a similar way using Supabase and SQL and PGVector. You can easily convert our Colab to Streamlit or Gradio. That's not an issue, but I want to show you this framework, which might be more relevant to production level settings. So I'll come back in 2 to 3 minutes for our last segment now. All right, everyone. So let's continue. I'm going to close some tabs over here so that does not appear too cluttered. Okay, so actually this Google Colab code, not Google Colab, this Drive link which I've shared with you, right? This is going to be our main guide for how to do this deployment. And if at any point, if you find the front end or back end part too confusing, don't worry about it. Because the main purpose of this workshop is not to teach you those things, but to really show you the workflow of overall how it is done. So first thing what we have to do is that just go to this Supabase SQL editor and copy this. Go ahead and copy this entire thing which I am copying right now. Okay. Once you have copied this, the next thing which you have to do is go to Supabase. Go to Supabase and you will need to create an account over here if you already don't have one. And then you can click on start your project. So I am going to create a new project here now, which is let's say Visuara AI RAG workshop. And you will also need to give a password here. And then you can change your region to wherever you are associated with. So I'm in Pune right now. So I've changed the region to Mumbai. But based on the region which is closest to you, you can right now change it. Ideally, this region should be where your users are based. But we are not going to deploy it for clients right now. So just change this and click on create new project. Can you tell me once you have reached this point where you have created a new project and you see something like what I am seeing right now on the screen? You have reached? Okay, good. So basically for others who have not reached, we just went to Supabase, created an account and created a new project. Next, go to SQL editor over here and copy paste. Actually, I think I did not copy paste. Yeah, we have to copy this. Copy paste this thing. Now, I can explain to you what we are doing here. Basically, the first thing is we are creating a table. This table will consist of our chunk and it will also consist of our embeddings. Okay. If you also want to convert images to embeddings, you need to make one more column here for image embeddings. Now, what we are doing here is that we are using IVF flat. Remember, I mentioned to you about IVF flat indexing. We are using that and we are combining this with a similarity search function. So this match documents is going to be the most important function which we have defined over here. This is an SQL function and what it does is that it takes our query embedding vector and from our chunks, it retrieves the top 5 chunks which are closest in cosine similarity to the query vector. And we are using an OpenAI embedding model which has the dimension of 1536, which is twice the length of what we have used the sentence MPNet model. That's it actually. That's the only thing which we are doing over here. And then the rest of the thing mentions how this match document function actually operates is that it takes the cosine similarity, calculates the cosine similarity and it restricts the top chunks. That's all. So in this SQL code, we have done two things. We'll first create an empty table. Then I'll show you how to upload the embeddings of our chunks into that empty table. But then finally, when we do the retrieval, we are going to use the match documents function over here. So we just have a simple SQL function over here for matching the documents. This is the advantage of using SQL editor, right? All of these functions can be very simply written. Next, what you can do is that you can click on run over here. Click on run and you will see success, no rows returned. How many of you are seeing this right now? Success, no rows returned. Okay, that is good. Now what you can do after this is go to the table editor and you will see that chunks table has been created, which is fully empty for now. Completely empty table has been created, right? Which has the chunk index, it has the content of the chunk, it has the metadata, and it has the embeddings. All of these are the columns which we have to fill basically. How will we fill those columns? We'll fill those columns when we upload our document chunks to this table. Okay, so our first milestone is all of you should reach this table. There is some, is the database created in Postgres? Yes. So Supabase is Postgres SQL database. So I think Sanket has got an error. I don't think you should be seeing that error because none of you have got that error yet. Okay, if you have reached this part, our Supabase part currently is over. You can next, we are going to go to VS Code. How many of you have VS Code installed? Yes, okay. So before you doing anything in VS Code, actually go to your desktop and create a new folder. This is where all of our code is going to live. So you can create something like nutritional rag workshop or whatever you want. Okay, create this folder over here. So Supabase is the name of the application. Think of it like a product, right? It uses Postgres. That's the difference. Okay, so if you have created the table, then created this folder, the next thing you have to do is go to VS Code. I hope all of you can see my VS Code screen. What you have to do here is just click on the left hand side and click on add folder to the workspace. And then you can just add this empty folder over here. How many of you have reached this step? Oh, Manoj, you created an account in Supabase, right? So basically what we did after that point is once we created that account in Supabase, what you have to do is make a project and then copy this thing, go to your project, go to your SQL editor, add this in the SQL editor and just click on run. That's it. Please explain VS Code. Yeah, so in VS Code, what we did is we first on your desktop, we created a folder. You give it any name. Then you go to VS Code. And on the left hand side, you will see something empty, right? There you click on add folder to workspace and then select that folder. So that folder will then be added over here. It will be an empty folder for now, but you will see it. Good. Next step, what we have to do is that we have to define a file called ingest.py. This is our main file. What this file will do is that it will download the documents. What it will also do is that it will create chunks and it will also embed the chunks. So it will do many things together. And the code for that you will find again in our drive folder. Go to our drive folder and you will see this ingest.py, right? Just copy this and paste it over here. Okay. And now what you'll also need to do on the left hand side is upload the PDF. So we have this nutrition PDF, right? Just upload it to our VS Code folder. You can do it on your folder or you can do it in VS Code itself. So here you can see on the left hand side, I have uploaded this PDF over here, right? This is that folder this is that file which you should be uploading. So this file should be present in your folder right now. How many of you have reached this step? Done? Okay, good. So let's quickly see what this ingest.py is actually doing, right? So first thing what it's doing is that, let me put this thing down. First thing it does is that it actually takes my text and it cleans my text. So it reduces, it removes white space, etc. And here we are doing chunking. So we are making 20. So you can even do 10. So let's do the same thing. Let's do 10 sentences in one chunk. And here we are doing overlap across chunks. So what this code will also do next is that it will chunk a page by sentences. It will go through each page and it will create a chunk of 10 sentences per chunk. So it will assemble 10 sentences, put it into one chunk. This is the same thing what we did in the code, by the way, if you remember. So that's the chunking. So if you look at specifically what is happening, we are first reading the PDF, right? The PDF which is uploaded, we are reading the PDF. Then what we are doing is that we are chunking the PDF 10 sentences per chunk. When chunks are built, the next thing we have to do is we have to convert those chunks into embeddings. And the embedding model which we are using is text embedding 3 small from OpenAI. So we are using an embedding model here where we create these embeddings out of every chunk. And then in the last step, what we are doing is so remember in our Supabase table, there are these rows like document ID, chunk index, content, metadata, and embedding. So if you go to our Supabase table, it has document ID, chunk index, content, metadata, and embedding, right? We just want to populate all of these. So we are adding the doc ID, index, and the content, metadata. Remember, what are we collecting as metadata? We are just collecting the page number, I think, or the chapter number, really. We would have mentioned it somewhere. But yeah, we are collecting metadata as page and the source. And here is where we are uploading the chunks to Supabase, right? So this is that point when chunks will be uploaded to Supabase. Did everyone understand what this function is doing? Essentially, in the Miro board, we have seen the steps, right? First is file loading, then creating chunking, convert it into embeddings. Just one new step here is that we are uploading these embeddings into Supabase. That's the new step. Everything else you already know. How is this code connected to my account in Supabase? A good question. Let me show you how that's connected in the next step. In fact, we have not even uploaded the OpenAI API key. So here create one more file and you can name it as .env file. In this env file, we have to basically add three things. I'll show you what to add in this env file. In this env file, we have to add our Supabase URL. We have to add our Supabase service role key and we have to add our OpenAI API key. So let me mention the three things to add here. Supabase URL, Supabase service role key, and the OpenAI API key. OpenAI API key, you will need to get it yourself. I'll show you right now how to get the Supabase URL and the service role key. So go to, I'll need to remember where to find this. So basically go to database. Oh, not database. I think you have to go to project settings. Go to project settings and go to data API. This URL which you see here, this URL, that's your Supabase URL. So upload this URL over here. Next thing is go to API keys, and here you will see this service role secret. Click on this reveal and copy. That's going to be your Supabase service role key. And OpenAI API key you will need to enter yourself. Did everyone understand where to get the Supabase keys? So go to project settings. Yeah, let me show again. So you are currently on this page, right? This is not the correct page. Go to on the left hand side menu, go to project settings. In the project settings, you will see different things here, right? First, we have to go to data API, then we have to go to API keys. So go to data API over here, and this is my project URL for Supabase. Copy this. It will be something like .supabase.co and paste it over here. Next thing, go to API keys, click on service role, click on reveal and copy this. That will be in your service role key. And how many of you have your own OpenAI API key, by the way? You should have your OpenAI API key to run this code. Okay, if you don't have your OpenAI API key, what you can simply do is go to platform.openai.com, click on settings over here, click on API keys and click on new secret key. And then you can do something like create secret key, and then you can get this for yourself. Okay, you'll need to add some money in your account. I think just add $3 or $5. That's a good joke, Peter. So next, what we have to do, how many of you have reached this step where all three files are there? Where you have uploaded this environmental file. You have reached this step. Okay, good. What about others? Okay, good. OpenAI API key, what's the step? So OpenAI API key, just go to platform.openai.com. Go to settings. Go to API keys and create new secret key. All right. So now what we have to do is that go to ingest.py, and actually before running this code, we have to install these packages. So just copy this and install and paste it in your terminal. So you can see that I have installed all my packages here. Once you install the packages, again, you can clear the terminal and then just run python ingest.py. So this will run the ingest file, and hopefully if it runs correctly for you, all your chunks and all the information will be uploaded to the Supabase table. Can you use Grok? Yeah, but then you will need to use Grok embedding model, I think. So you loaded, how many of you loaded the packages? Package loading, if it's done, can you mention in the chat if package loading is done? Yes, okay, good. Now just run this python ingest.py. Hopefully, if everything is correct, things should directly start working at this point. But if there is some mistake, let's see, we'll try to debug it. So see, my chunking is now done. Now I'm in the process of embedding. For you, if you have uploaded your API keys correctly, ideally you should also start seeing something like what I'm seeing on the screen right now. Okay, now once embeddings are created, the last step is we are uploading these embeddings to Supabase. So see, we are uploading all of our embeddings to Supabase. How to resolve dependencies. So ideally you should not, yeah, that's just a warning. So just you can ignore the warning if you're getting dependency issues for now. Yeah, it's good, Praveen, you shared the requirement.txt file. Okay, so now for me, everything is uploaded to Supabase, right? So ideally I should go here now. I can check my table and I can check my chunks. Uh, Let me refresh this. Okay, so for some reason it is still showing empty. SQL. What about others? Are you able to see something in the database? Ideally, you should be able to see. I think I've connected with my, uh, I don't know which, um, inserted. So ideally, chunks should be inserted over here, but I think my dot environmental file is corrupted. Let me again check once more. If a new key is generated, so you go to project settings. Let me try this again. So I am now running this again with an updated environmental file. I can see that Sandeep has got an error over here. I think your file is somewhere else, Sandeep. Can you make sure your file is in the same place as ingest.py? Oh, if it's in the same directory, I'm not. Did you install the package PyMu PDF? Okay, so let's see if this still does not work for me. I'll use my other project in which I had already created. Yeah, I think for some reason I'm not able to see this. Where was it? Oh, it has populated over here. Okay. I think I was looking at a different um, I was looking at a different database or a different project. So ideally, if everything is working for you now, you should see something like this. You should see an ID, you should see chunk index, you should see content, metadata, and embedding vector like this. How many of you see this in your table? Can you confirm right now? In your table, are you able to see all of these columns? Okay, good. Now the next step, what we have to do is that just inspect these ones. This is the advantage of PGVector plus Postgres, right? All your embeddings, all your metadata, your content, it stays in one place. So that's the real advantage of this. Okay, so now what we can do after this point is that we can do the next step, which is now we need to connect it to a front end basically. By that, what I mean is that we need to, let me go to my Miro board. What we need to do is that, so we have finished this part. These two things we have finished right now. Now we have to make the backend and the front end API, right? So this is going to seem a bit new for some people who are not used to front end and backend. But for now, it's just important that you follow the instructions. So to create the backend API, what you have to do first is that in this nutritional RAG chatbot, just create a new folder called rag-chat. Let me check if that's the correct one. Yeah, create a folder called rag.chat. And then what you have to do is that go to our drive, and then we are going to use next.js. So there are some instructions which I have defined to create it. So just run these three commands. Basically, this will create a next.js application within your particular folder. So run these three commands here. Just copy paste this full thing into VS Code, right? Like I have done right now. So it's done for me right now. You will see some things like you can click on yes on every single prompt which shows up. Yeah, first will be to install Node if you don't have Node. But let's see, can all of you try doing this on your VS Code and see, report to me if what you are seeing basically. So from Supabase onwards, right? What we have done is that we have just created this file called ingest.py, and that you will get on the drive folder. Then we have added this PDF. We have created a .env file where you have the Supabase URL, service role key, and the API key. That's all. And then we have run this ingest.py. When we run ingest.py, all the tables are uploaded on our Supabase like something like this. How many of you ran these three commands? If you have successfully run these three, you should see that in the RAG chat folder. Now, okay, I think nothing is updated for me over here. Let me again go to. So ideally, what should happen is that yeah, you should get all of these. Yeah, and once this installation is done, you should see this kind of files automatically coming over here in your rag-chat folder on the left hand side. If you are getting npx command not found, you will need to install Node.js. So after ingest.py, what we have to do is that we have to create this folder called rag-chat. So create this folder here, like going to here and create new folder. And then what you have to do is that you have to copy these three functions. You have to copy these three functions and you have to paste it in the terminal. Once you copy these three functions and paste it in the terminal, then you should directly see this rag chat folder populated by all of these files and folders. This is what we'll be using to make our front end plus backend app. Where can I find? So these functions are in the drive folder. When we see next.js, there is a file called next.js plus lovable deployment instructions. Here you will see these three functions actually. Just copy this and paste it on VS Code. Drive folder. So I've already shared the drive folder link on chat. I'm just sharing it once more. So it's asking which liner would you like to use, right? You just press yes to everything. Just press enter to everything. All the questions which you get when npx is being installed, you can press yes to everything. So it will ask many questions like, would you like to use, just press enter. Would you like to use Tailwind CSS? Just press enter over there. You'll get all these 6 questions. At that time, just press enter. So don't worry about this too much. How many of you have reached this step where you see this folder called rag chat and you see all of these files within this? I'm waiting here for some time because this might be a bit difficult. Also, this is a bit of front end, back end stuff, right? So even if you don't understand this, it's completely fine. Okay, so now I'm going to move ahead. The next steps are a bit more detailed. So we just have 2 more steps actually remaining. Okay, so pay very careful attention over here. Now, in the rack chat, we have to basically create a file like this. So in the rack chat, you'll see an SRC, right? There is already an SRC. In that, there will be an app. There you have to create one more folder called API. Within that, you have to create one more folder called chat. And then within that, add a file called route.ts. And that file you will get over here. Here, this is that file which you will need to add in that specific path. So I'll show you how that is done. So go to app, click on folder, click on new folder, call it API. Within this, again, click on new folder, call it chat. And then you can just upload, you can first download route.ts. I think I've already downloaded it. Yeah, but I don't know from which. So in fact, you can just go here, download this. And once you have downloaded it, yeah, just drag and drop this into that chat folder. That's it. Then you should have this route.ts. Did you create this route.ts file? Could you mention in the chat if you have created this? So if you see what's actually happening in this route.ts file is that this is where all of these steps which we saw, that whenever you get a query from the user, it gets converted into an embedding and the match function is called. That is happening over here. So if you see uh, the user query is first converted into an OpenAI embedding. That's the embed query function. Then what you have to do is that you have to call the match documents function from Supabase. So you have this query embedding, right? You have to call this match documents. And what this function will do is that it will go back to that SQL editor which we have defined in Supabase over here. And it will get this match documents function and it will retrieve those chunks now in our database. If you go to the table editor, it will retrieve these chunks. It will retrieve the embeddings from these chunks which have the highest similarity score. That's what's happening in this route.ts file over here. And here we also give something related to context, like I couldn't find this in the relevant provided context, etc. So essentially what all chunks match from this Supabase function, they go into building our context and this context goes into our prompt. And then we again call chat GPT OpenAI completion to fulfill our request. So here is where all the retrieval plus generation is actually happening. This route.ts is the main brain essentially of what we saw in Google Colab. That's happening in only two files. One is ingest.py, where embeddings are happening, chunking is happening, and embeddings are uploaded to Supabase. Second thing which is happening is in this route.ts, where user query is getting embedded. We have this match documents function which retrieves the relevant chunks. Then we construct a prompt to the LLM, where first, based on the relevant chunks, we build the context, then pass it to the prompt, and then ultimately, this is the main thing which generates the answer. You are a strict RAG assistant, answer only using the context. If the answer is not present, say I couldn't find this in the provided context. Cite sources like 1, 2, and include page numbers next to each claim. Now, the last thing which you have to do before we run this is this page.tsx, right? You can delete this. Delete this page.tsx, and you have to upload this. So this page.tsx just consists of the front end code. Like user has to type something. So essentially the chatbot like simple interface. So this you can go ahead and upload over here. Is this clear to everyone? How many of you have reached this step? Because those of you who have reached this step, this is the last step actually. After that, we have to just run the npm run dev command and we are good to go. So I've deliberately tried to make it a bit simpler. So what you can do, those of you who have finished this step, just go to your terminal and now just type npm run dev. Okay, Mayank, now you have started seeing that screen, right? That's good. That's exactly what we should be seeing at this stage. Now, before you do anything on that screen, uh, let's first wait for everyone to reach this part. Where did you get those .css? So those were automatically created when we ran these three files, right? When we ran these three commands, those files were automatically created. So now if I go to this local host over here, hopefully I should see something. Yeah, this is ideally the screen which all of you should be seeing if you have done all the steps until now correctly. Before we actually test the chatbot any further, what you can first do is that first let us check whether everything is working or not from Supabase. So the last file which you can download is this file called testembeddings.py. Just go ahead and, or you can just double click here, copy the content, and just below ingest.py, just create a new file called test. Uh, yeah, just create a new file called testembeddings.py. So here we'll just check whether things are working or not. It's the same workflow as what we saw in route.ts, but it checks whether things actually work. One more thing actually which I forgot to mention is that those of you who reach the end, right, in this rack chat, you will need to create one more file called .env.local. .env.local, and here you will need to upload the same env configuration as you saw over here. So otherwise it will not work. So just create this .env.local and add the same configuration. Now, before actually we run anything on the front end, we can actually check whether things are really working or not, right? So we can run this test embeddings.py. So Python test embeddings.py. Yeah, I think I'm getting these no matches because my environmental file let me use it from some earlier project which I had created. But for all of you, this should ideally work. Can you, if any one of you has run the test embeddings.py, can you type your responses in the chat? Yeah, see, this is now working. This is ideally what you should be seeing. So in the test embeddings.py, what we are essentially doing is that we are just testing whether things are good or not. We have this following queries. We have embedded these queries, or rather what we are doing is that we are doing this match documents function from Supabase and we are returning the rows which have the maximum score. That's all we are doing. So we are just checking whether for some questions things are working or not. So let's see this question, right? How often should infants be breastfed? Let's say if this is the question, you will see that on page 884 there is the correct answer and which is actually true. So this answer is the correct one. If you see what are the symptoms of pellagra, you will see that symptoms include nausea, muscle cramps, confusion, dizziness, etc. If you see how does saliva help with digestion, you get correct pages which are retrieved. So how many of you have reached this step? Oh, Amit is saying not allowed to install. Oh, I don't know why Node.js is restricted on Office laptop. Okay, so Mayank, if you have reached that step, your thing is working perfectly for now. David, your thing is also working very nicely. For Sandeep, what's the, oh, you are getting a script error, is it? The npm run dev. So ideally, if everything has been installed correctly, can you check your package.json to see if it has this dev? Okay, now, uh, yeah, I think Amit, you should definitely get a new laptop in that case, if it's not allowed on Office, because if you are planning to implement this in production, it's highly important. For Nishkarsh, I think the answers are very good. Good for Nishkarsh, David, Liju, all of you have got good answers, right? Just make sure that before, can you actually make sure that in your rack chat folder you have this .env.local? Unless you have this file, nothing will work for you. So just as we had this .env file in our main folder, we should also have the .env.local in our RAG chatbot. Now, those of you who have reached till this step, just copy some random question, copy some question which you want to test, right? Let's say symptoms of pellagra. Let's say this question is there. And what I'm going to do here again is I'm going to ask this question into my chatbot. So what are the symptoms of pellagra? And you can send this question over here. I couldn't find this in the provided document. The reason it says this is because the similarity score is a bit low. You can also ask other questions. How does saliva help with digestion? Let's say. Go ahead and ask this question. So here you see, we get the response that saliva helps with digestion by acting as a natural mouthwash, and it actually gives the references, page number 1125. Let us check whether it's actually present on page number 1125, right? Page number, yeah. So page number 1125, what's being referred to right now is oral disease. Oral health refers not only to healthy teeth and gums, which is exactly what we see over here. So the pages which are being retrieved by our chatbot are correct. Similarly, you can ask different questions, right? What is the RDI for protein per day? Or how often should infants be breastfed? Let's say if I ask this question, you will again see if the similarity score is a bit low, it will say I couldn't find this in the document. What is the RDI per protein per day? So if you don't want this statement, I couldn't find in the provided document, you can also change your prompt a bit. In the prompt, we have specifically mentioned this, right? If you don't want this statement to come again and again, and the last thing which I will ask is what are macronutrients? So all of you who have reached this stage, you can uh, try to check all the prompts which I am testing right now. Oh, Praveen, you have got good answers. Nutritional. So now one thing which we can do is that if you are checking that, if you are getting the thing that I cannot find this in this document, let's actually change our prompt a bit. So we can go to our route.ts and we can change the prompt slightly. Let's remove this. Okay, and now let's see. Now I've removed from the prompt that answer like, because all the time it's answering not present. So let me ask this again now. Let me ask this again. I think this is there in one more place. I couldn't find this. Yeah, it's there here. Let's say I remove this also. Yeah, I'm still getting the same answer. I couldn't find this in the retrieve document for some reason. I'm sure it has to do something with the prompt. Let me say always. Oh, I think I'm on a different folder. Yeah, I think I was making changes in a different folder. Let me make changes in the correct folder. So I should actually, this is my new folder which I have created. And now here I will go to route.ts and let me change this over here. Let's see. So now I've made the change in the correct document. I just want to see whether it gives the same. I couldn't find this. Yeah, see now it gives the correct answer. And here the similarity score looks to be quite good. So I don't want unnecessarily the RAG chatbot to say that don't I don't find this in the document, right? So again, this points us to prompt engineering. If prompt engineering is not done properly, then things won't usually be good. Here it's fine because the similarity score itself was a bit low. Now, if you observe that the similarity scores are not good, you can go back here once more and you can even do things like semantic chunking or uh, structural chunking, whatever. You can explore it further after this point. Sorry, did you run the test? Yeah, I ran the test embeddings.py script actually. So if you run the test embeddings, text embeddings.py actually gives you an idea of what you will see on your front end. What you see on your front end is just a reflection of what you see when you run this test embeddings.py script. Now, one last thing which I want to mention over here is that first of all, how many people saw this front end? Can you mention in the chat that you have been able to develop this and you are seeing responses? Yes, right. It's good that many of you have reached the end. That was the main goal of this section. I think many of you are also seeing better answers than what I am running right now. Where are all the steps of these applications? So all of this is mentioned over here exactly in this Google Drive link. Now, one last thing I want to mention is the ingest.py file, right? You can make the ingest.py file slightly more complex by adding an embedding column for vision. So many of you ask questions about how to deal with images, right? What you can actually do is that you can define two models. You can define a model for you can define an embedding model for text, and you can define a vision embedding model also. So basically PyMu PDF can extract images, for sure it can extract images. You just, so then the extracted images you can convert as vectors, and you can upload this also to Supabase. So here you have a, if your client also wants to, also is interested in maintaining a reference of the data, you can also maintaining a reference of the images, you can also convert images to vectors and add those in the Supabase table as well, right? So this is how you can additionally create embeddings for multimodal data representations. Where is this file? So this file I have not actually added anywhere yet. But what I will do is that I will just add it right now on here. Okay, good. So now we are done with this. I think many of you managed to see the front end, right? But last thing what we want to do now in this tutorial is that lovable. Now what I want to do is that I want to show you the power of lovable. So go to lovable and I will tell you the exact prompt which you have to write over here. But first, when you are on lovable, uh, click on the Supabase here and click on you need to connect your Supabase project basically. So I think the project which I should connect is this Visuara's AI project. Visuara's AI project. Okay. So Supabase is now connected. Now I'm going to tell you what is the prompt which you should write. Essentially, Lovable is this awesome tool. Now, if you see this front end, it's not looking very cool, right? What if you want to make the front end which looks something like this? This uh, font is actually inspired from this ArcAGI website. So I want my front end to look as cool as this, and we can achieve this in Lovable using just simple prompt engineering. So let me show you how I've mentioned all of the things over here. So first thing you have to tell Lovable is that, hey, here is my SQL editor. Here is my SQL editor code on Supabase. Then go to Supabase, go to your SQL editor code and just copy this and add this full thing over here. Okay. Next, once this is done, you have to say that uh, you basically then have to give your, I have a script called ingest.py, which has the following files. So I have the following files, say this, and now you have to upload essentially the code of all of your files. You give this, and then you upload the code of um, ingest.py. You go here, you get ingest.py, and you upload this full thing over here. Then what you do is after this point, when ingest.py is uploaded, next thing you can do is I also have page.tsx. And then go to page.tsx, upload this thing. And I also have route.ts. and then upload whatever you have in the route, which is basically here. And then what you say after this is something related to the UI. Okay, basically also tell it that I have this text embeddings, test embeddings. Don't need this, but yeah, you can say this. And then after this, you have to say that with respect to the UI, right? So you will already have my Supabase keys since I've connected my Lovable account. You can prompt me to enter my OpenAI API key. Never share the OpenAI key directly. Then make the look of the website very cool. The chat interface should look minimal and sleek. Then show three dots when responding. Show citations when you have pages to cite. I mean clickable sections. When I click on it, a small pop-up highlighting the place from the text it was taken should be shown. Then instead of, I can give any name. Instead of nutrition AI, can you give the name as RAG nutritional chatbot built from scratch presented by Visuara? Then finally, I say make the theme of the text and font exactly like this RKGI website. This theme is very, very important to follow. Also show small sounds when three dots are coming and small sound when the response is generated. So let's see, let me put all of this and then let's click on run. Earlier, I was not sure whether this would work or not. And honestly, it does not work all the time. You need to fix many errors as it comes. But I was able to get this website. If all of you can go over here, I was able to get this website through simple prompting. We do not need VS Code. We do need VS Code actually, because the functions which we are generating, Lovable needs access to those functions, right? Those functions we have to define in VS Code. First, check whether everything is working on VS Code. Only when we want to improve the front end design, that's when we go to Lovable. There is a question on how to connect. So here, see, I have to enter my OpenAI API key over here. So then what I do is I enter my OpenAI key here and submit. And now Lovable is working. Is Lovable connecting to our VS Code files? No, we are uploading the VS Code files manually. So the reason this prompt has become so big is because we are uploading all our files manually, because Lovable does not take .py files, unfortunately. Otherwise, we would have directly uploaded the file. Now, how to connect Lovable with Supabase? I think there must be a tutorial for this, but it's actually quite simple. There is just a simple click of a button, I think, Aman. So there would be an option to connect it to Supabase actually. So actually, through all of these prompts, I got this website whose link also I shared it in the chat. This website is now implementing the exact same pipeline which we had discussed. So it's implementing this RKGI theme, which is of course pretty cool. And it's having these small sounds, right? When the response was generated, I have small sounds. And it also gives sources along with the response which it is generating. So if I ask, there is a small sound, if you notice, then it has these three dots for thinking. Then it has these responses and it has sources at the bottom. Actually, these links were also clickable. I don't know why they are not. These sources, these page numbers were clickable earlier. I am not sure why it's not working now. But just with the simple VS Code front end, back end, and Lovable integration, we are able to build websites as cool as this. Earlier, to go from VS Code to a website which looks like this, it would take a huge amount of UI integration. I would need to learn about material UI, front end, back end. But now these tools actually make it a lot simpler for me, right? So Lovable might take some time and it might make mistakes also. Um, let's see on which stage are all of you right now? At the end, to improve RAG, we can play around with different chunking. Yeah, to improve RAG, you can play around with all the things which I mentioned towards the end of the class. You can play around with chunking strategies. You can play around with embedding models. You can play around with data ingestion pipelines. You can also play around with how you're storing metadata. So currently we are storing the metadata, which is just the metadata we are storing is just some random things, right? We are storing maybe the page number and the source. But the biggest advantage of Supabase and Postgres is that the metadata is stored along with the embeddings. And all of the other data is everything is in one database. So things become very easy to mix and match because in SQL you can easily query rows, get things from rows, etc. Yeah, so this is the chatbot so this is all live right now. What I'm seeing right now on the screen is what Lovable has given to me. It's already pretty cool, but I think there are some mistakes here on my front end. What about others? How much of it is finished? Okay, so Mayank has got the chatbot. Just check whether it's working or not. Does user queries or no? User queries are not stored by default. We'll need to uh, specifically add that if you want it to be saved. So now my lovable says that it's done. Let's actually check whether it's working or not. So what I'm going to do is I'm going to take the same question and I'm going to ask it here. Oh wow, so this actually generated it quite well. So see, this I built live right now. I did not know it. Sometimes it's stochastic, sometimes it works, sometimes it does not. So you can click on this right now and you can actually get the reference here. You can click on this and get the reference here. Uh, and now you can even actually publish this. So if I want to publish this, um, yeah, let me just say publish. I think Liju has got an answer. Oh wow, that's great. Yeah, this is very nice. But your citations, are they clickable? Ideally, it's good to have clickable citations. So my site is also published right now. Citations, yeah, this is this is what I get, and I can ask something random over here also, like let's say what are macronutrients? Yeah, so now it's answering actually pretty well, and it's given me these references which are clickable over here, and it also shows me the page where it appears. So first it shows page 2, page 3, etc. Wherever there is a similarity, higher similarity score, I see the results appearing over here. Oh, Mayank has also got his answers. Great, that's amazing. Can both of you put your published links on the chat? I will also click on those and check it out. So I think Mayank and Liju, both of you, can you put your published links? So just go to publish, or you can even put your preview link. Yeah, so let me click on. So this is Mayank's RAG chatbot, right? And if you randomly click on something, well, it's not being clicked for me. So let me, oh, it is being clicked. So let me type this. Yeah, this is amazing. So we get 5 references over here. Some of these references are not quite accurate, but with that is because our RAG system itself needs to be improved a bit. But now you see how this is all linked to production, right? I hope all of you have started to appreciate the link between the Supabase database, then Postgres SQL, plus how we use PGVector. The reason Supabase knows to use PGVector is if we say if not exists vector. So this enables PGVector actually. PGVector helps us to create embeddings which are stored in the Supabase database. Oh, I have links from multiple people. That's nice. This color scheme is nice. And this link also is also nice. So for others who have not reached this stage so far, I really encourage you to try this after this answer is actually correct because it's taken from this data set. I remember reading this 3Ds. So let's see actually on the data set. It's 4Ds. But at one place, I think there's one more. Yeah, this 4Ds. But whereas here it says 3Ds. So 1D is missing. But anyways, I think we are retrieving this from our knowledge base. Says ran out of credits. Yeah, so that might happen on Lovable. It's a good idea to subscribe to their plan. I think I use Lovable a lot. All right, everyone. So this brings us finally to an end of this workshop. So today also it was around 4 hours and yesterday 3 hours. But now I think we are at a place where all of you who have stayed till the end, I want to thank you for staying for such a long time, that too on a Sunday. Our whole morning is essentially spent in this, right? 8 to 12. But I think it's worth it. Like usually RAG tutorials are covered very quickly. But I hope that now totally when you revise the material, it will be around 7.5 hours. So this entire material, it's from fundamentals, right? So now you will never be scared of RAG related applications because you know how it works from scratch. And I hope you also know how to make engineering choices at various levels like document processing, chunking. Then what are the engineering choices to make at the embedding level? What is the difference between IVF flat and HNSW? All of these things are usually glossed over. So I did not want this to be a quick workshop. I have also shared this prompt engineering guidebook, not prompt engineering, the chunking guidebook from Visuara. And today we saw evaluation at the end. And finally, I wanted to show you how production level rack systems are built. So for that, we need to come out of Google Colab and we need to go into VS Code. On top of that, if you are building a rack system, please consider Supabase or Postgres also. These are some of the best tools, production level tools actually. So I hope now your production level journey starts after this point. And I really hope many of you get into research because other people, they directly use things like vector databases, right? But our main focus should be on indexing. That is like having a research mindset. So not just blindly using vector databases, but learning about IVF flat, HNSW, and then thinking about how can we make this better? How can indexing be improved? Then you can also play around with, it's called ablation studies, right? You can play around with various things which I've mentioned over here. And you will maybe discover a chunking strategy which works for multimodal embeddings. And that might be a research paper for you. So whenever people claim that they have done a RAG project, I always ask them these detailed questions which they have no answer to, right? Because they would have followed a 10-minute or 15-minute tutorial. That's not a good way to do it. And now, as I mentioned at the start of the lecture also, we are slowly moving towards this context engineering kind of a domain, right? So I'm planning to also release some blog posts and post on context engineering as a whole. And in our live lectures, in the production live lectures, our next thing is going to be agents. Or I'll think about it. Maybe I'll talk about multimodal embeddings first, or we'll go to fine tuning or agents. But anyways, memory is going to be a critical thing, which I have not covered so far. How to manage memory. One more such workshop which I'm planning to make is related to GPU programming. But that workshop, I want to keep it restricted to people who have done the build LLM from scratch course and know about practical aspects, because that will be a very in-depth kind of a course. So all these things will not be, you will not be able to understand unless you know about the attention mechanism, unless you know how tensors operate, etc. So I'm planning to conduct a workshop on this. Let's see. I'll plan to make it as detailed as this one. Resources. I'll be sharing all the resources, so don't need to worry. Yesterday, can you confirm if you received my email? All those who registered externally through TopMate, I had sent an email to all of you yesterday with the recordings and lecture notes, everything actually. If you have not received an email, send me a message at hello@vijwara.com. Now, after today's class, I will also be sharing the recording with you, the drive link also. So you will have all the material which you need to replicate if you have missed something. When are you planning to launch that GPU? So this GPU workshop, I am planning to do it in a collaborative learning manner, right? Like if I learned something, I would directly have a lecture where all of us can learn together. Because honestly, I am also a bit new to this. So in my opinion, the world is moving towards two things, right? Parallelization and quantization. And I want to master both these things because transistors are not getting any smaller. Moore's law is almost dead. So how else can you increase the speed of processing? Only two ways remain, to parallelize it or to quantize it. This is a good playbook for parallelization and GPU programming, I thought. But yeah, I plan to have it in a shared collaborative kind of a class. But in that class, I only want people who have knowledge of attention mechanism, let's say, or who have covered the build LLM from scratch they have watched, and also maybe the build DeepSeek from scratch, because we'll directly start from advanced things in that, maybe next month or so. All right, everyone. So it's almost 4 hours now. So I'll stop this lecture at this moment. Thanks again, everyone, for attending and making this a great workshop. Also, I did not plan for this to be 7 hours. I had planned it for a 3-hour workshop, but I hope you all learned a lot. Because of the questions you asked, it became even more enriched. Thanks, guys. And I'll share all the information with you after this class is done. See you. Bye.